Welcome to day one of our course on Principles of Programming Languages. In this session, we will introduce you to the core concepts and importance of programming languages. A programming language is a set of instructions that allows us to communicate with a computer. It enables us to solve problems, create software, and interact with machines. Programming languages can be categorized into two broad groups: high-level and low-level languages. High-level languages are user-friendly, while low-level languages are closer to machine code. Additionally, languages can be compiled or interpreted, affecting how they are executed by a computer. Learning programming languages is essential for several reasons. It enhances your problem-solving skills, improves logical thinking, and opens up diverse career opportunities in fields like software development, data science, and artificial intelligence. Ultimately, programming languages form the foundation of the technological advancements we see today. Programming languages have evolved significantly over time. In the early years, languages like assembly and Fortran were used. In the later stages, languages like C and Smalltalk introduced procedural and object-oriented paradigms. Today, languages like Python, Java, and JavaScript dominate, offering robust frameworks for modern development. And as we look ahead, emerging trends like functional programming and quantum programming are shaping the future of programming languages. Programming languages follow different paradigms, which are approaches to programming based on certain principles. Imperative programming focuses on specifying the steps to achieve a task, as seen in languages like C and Java. Declarative programming, on the other hand, emphasizes what needs to be done, not how it should be done. SQL and HTML are common examples. Lastly, functional programming treats computation as an evolution of mathematical functions, which is seen in languages like Haskell. In addition to the paradigms we just discussed, we also have object-oriented OOP, which organizes code around data and objects. Languages like Java and Python utilize OOP principles. Lastly, event-driven programming focuses on responding to events or user actions, and JavaScript is a prime example of this paradigm. Now, let's put what we have learned into practice. We will start with a class discussion. Why do you think learning programming languages is essential? After that, we will create a timeline to visualize the evolution of programming languages. You will also get a chance to research 5 programming languages, classify them by their paradigm, and share your findings. And of course, a little fun fact. Did you know that Python is named after the comedy group Monty Python, not the snake? To wrap up day 1, we have learned that programming languages are the bridge between humans and computers, enabling us to create software that powers the digital world. These languages have evolved to meet the needs of developers, and the different paradigms help shape how we approach coding tasks. In the next sessions, we will delve deeper into each of these areas and build upon what we have covered today. Welcome to day 2 of our journey through programming languages. Today, we will dive into syntax and semantics, the fundamental building blocks that govern the structure and meaning of code. Let's get started. First, let's understand syntax. Syntax refers to the set of rules that define the structure of valid code. These rules ensure that the programming language is structured in a way that the computer can interpret. Think of it like grammar in human language. It ensures clarity and prevents confusion. Now, programming language grammar defines the formal structure of valid statements. This grammar can be represented using Bocas-Naur form (BNF) or extended Bocas-Naur form (EBNF). Syntax is crucial because it ensures that the code is well formed and can be parsed by the compiler. Next, let's explore semantics. While syntax defines the structure of code, semantics defines its meaning. It's about what happens when the code is executed. There are two main types of semantics: static semantics, which are checked at compile time, and dynamic semantics, which are checked at runtime. Why is semantics so important? Well, it ensures that a program behaves as expected. For example, even if the syntax is correct, the program could still produce incorrect results if the logic is flawed. This is where semantics comes into play, ensuring the meaning behind the code matches the programmer's intent. Let's compare syntax and semantics. Syntax deals with the structure of the code, while semantics deals with the meaning. For instance, missing a semicolon would be a syntax error, whereas using an uninitialized variable is a semantic error. When we look at error detection, syntax errors are caught by the compiler during compile time, whereas semantic errors are often only identified at runtime through testing or execution. Understanding the distinction helps developers debug more efficiently. Syntax can be divided into two main categories: lexical syntax and grammatical syntax. Lexical syntax deals with tokens such as keywords and operators, which are the smallest units of code. Tools like regular expressions and finite automata are used to recognize these tokens. On the other hand, grammatical syntax arranges these tokens into valid expressions or statements. This is where parsing comes into play, and context-free grammars are typically used to specify valid statement structures in a language. Here's an example of an arithmetic expression in Bocas-Naur form (BNF). This grammar shows how expressions, terms, and factors are combined to form valid mathematical expressions. It's the formal way to define how the language processes arithmetic operations. Let's put this into practice. In this activity, identify whether the following code examples contain syntax or semantic errors. This will help you sharpen your skills in recognizing and understanding errors at different levels of programming. Here are a couple of additional activities. First, write the grammar for variable declarations in EBNF. Then consider a debugging scenario where both syntax and semantic errors are present. How would you go about fixing these issues? To wrap up, remember these key takeaways. Syntax ensures the structure, while semantics ensures the meaning of your code. Both are critical for writing reliable, functioning programs. Using formal tools like BNF, EBNF, and parse trees, we can analyze and design more robust programming languages. Welcome to day 3 of our series on programming languages. Today we will dive into lexical analysis, the first phase of a compiler. Let's explore how source code is transformed into a format that's easier for a compiler to understand. Lexical analysis is the process of converting the raw source code into tokens, the smallest units of meaning. It's the first step in compilation, where the input code is broken down into manageable pieces for further processing. A lexer, also known as a lexical analyzer, plays a key role in this phase. It scans the input source code and identifies meaningful units tokens. By simplifying the input, it makes it easier for the parser to handle the syntax of the language. Tokens are the building blocks of a program. They represent the smallest meaningful elements of a programming language. For example, keywords like int, operators like equals to, or variables like x are all considered tokens. Lexemes are the actual character sequence that match a token. For example, in the token identifier, the lexeme could be x. Each token has its corresponding lexeme, which is extracted from the source code. Regular expressions are crucial when defining patterns for tokens. They help match specific character sequence in the source code. For example, we use regular expressions to identify keywords, identifiers, numbers, or operators in the text. Here are some examples of regular expressions used in tokenization. For example, we might use patterns like if, else, or while. For identifiers, a regular expression would look like AZ, A to Z, A to Z, A to Z 0 to 9 star. And for numbers, it's as simple as 0 to 9 plus. Lexical errors occur when the lexer encounters characters or sequences that don't match any valid token. Common errors include invalid characters or using reversed words incorrectly. These errors need to be handled carefully to avoid disruptions in compilation. There are several strategies for handling lexical errors. These include skipping over invalid tokens, logging warnings and errors, and in some cases, gracefully terminating the compilation process if the error is severe. Let's look at the basic algorithm for lexical analysis. It starts by reading the source code and attempting to match it to predefined patterns. Each match corresponds to a token, and once matched, it is added to the list of tokens. Lexical analysis also involves ignoring white space and comments, which are not necessary for the next phase of parsing. If the lexer encounters unmatched patterns, it reports them as errors and either skips or stops processing. Here's a simple Python lexer code example. It defines a function that reads the input source code, matches it to predefined token patterns, and generates a list of tokens based on the matches found. As you can see, the lexer function processes the input code character by character, matches it against various regular expressions, and creates a list of tokens, skipping over white space and comments. Here's an example of the lexer. For an input like int x equals to 42, the lexer generates a list of tokens keyword, int, identifier, x, operator, equals to, number, 42, and unknown, semicolon. Lexical analysis has a number of important applications. It helps with pre-processing by removing comments and handling macros. It also plays a crucial role in syntax highlighting in integrated development environments or IDEs. Additionally, lexical analysis helps simplify input for the parsing phase and contributes to code optimization by detecting early errors in the code. There are several tools available for lexical analysis. Lex and flex are popular tools for generating lectures. In some programming languages like Python, you can implement a lecture using built-in regular expression libraries. Lexical analyzers often work in conjunction with other tools, such as parser generators. For example, lexical analyzers are often integrated with tools like Bison or Antler to form a complete compiler pipeline. In conclusion, lexical analysis is a critical step in the compilation process. It helps break down source code into manageable tokens, making it easier for subsequent phases like parsing. Understanding tokens, regular expressions, and error handling is essential for building efficient compilers. Welcome to day 4 of our course on Principles of Programming Languages. Today we will be diving into the concepts of grammar and parsing. Let's begin. Grammar is a formal set of rules that define valid sequences or strings in a programming language. Think of it as a blueprint that specifies how different parts of a program should be written. In programming, we rely on grammar to ensure that our code is syntactically correct. Grammar plays a crucial role in programming as it dictates the structure of a language. Without grammar, we would not know if a piece of code was valid or not. The most commonly used type of grammar in programming is context-free grammar, or CFG, which forms the foundation for many programming languages. Context-free grammar consists of several key components: terminals, which are the basic symbols of a language, and non-terminals, which represent abstract concepts like expressions or statements. Other important components of CFG include the start symbol, which marks the beginning of any derivation, and production rules, which define how non-terminals can be replaced with other symbols. For example, an expression could be replaced with a term, or a term could be replaced with a vector. Parsing is the process of analyzing a sequence of tokens based on a language's grammar. There are two main techniques for parsing: top-down and bottom-up. Top-down parsing starts from the start symbol and works its way down, while bottom-up parsing reduces an input string to the start symbol. Top-down parsing starts with the start symbol of the grammar and tries to derive the input string. It works by using recursive descent or predictive parsing. It's often easy to implement but can run into issues with left recursive grammars. While top-down parsing is simple to implement, it struggles with certain kinds of grammar, such as left recursive ones, where a non-terminal refers to itself in the production rules. However, it's still a fundamental technique in many parsers. Bottom-up parsing takes a different approach. Instead of starting with a start symbol, it tries to reduce the input string to that symbol. Shift reduce parsing and LR parsing are common techniques used in this method. Bottom-up parsing is more complex but powerful, especially when dealing with more intricate grammars. It's capable of handling more types of grammars compared to top-down parsing. Parse trees represent the syntactic structure of a string derived from a grammar. They show how a string can be decomposed into various components based on production rules. Here, for example, the expression 2 plus 3 times 4 would be broken down in a tree structure. Here is a visual of a parse tree for 2 plus 3 into 4. As you can see, multiplication has higher precedence than addition, which is reflected in the tree's structure. Each level of the tree corresponds to a rule from the grammar. Abstract syntax trees or ASTs are simplified versions of parse trees. They remove unnecessary details, focusing only on the key elements needed for further analysis, such as semantic analysis or optimization. Here is an example of an AST for the expression 2 plus 3 times 4. Unlike the parse tree, the AST eliminates unnecessary nodes and focuses on the core structure representing the addition and multiplication operations clearly. Errors during parsing often arise when a token sequence does not conform to the grammar. These errors could be caused by unexpected tokens or missing elements such as parentheses or operator. To handle these errors, parsers use different recovery strategies such as panic mode, phrase level recovery, or error production rules. Each approach helps the parser continue processing and even after encountering an error. Let's look at a simple example. This grammar defines basic arithmetic expressions. An expression can be a term and a term can be a factor multiplied or added. This CFG allows for the creation of expressions like 2 plus 3 times 4. Here's the parse tree for the expression 2 plus 3 times 4. Notice how the multiplication operation comes before addition, reflecting the precedence defined by the grammar. Parsing plays a vital role in many areas of computer science, especially in compilers, interpreters, code linters, and database query parsers. It's essential for understanding and processing programming languages as well as validating inputs. Thank you for your attention. That concludes our session on grammar and parsing. If you have any questions or feedback, feel free to reach out to me. I look forward to our next session. Welcome to day 5 of our course on programming languages. Today we will be discussing the key considerations in language design, what makes a programming language successful, and the trade-offs involved in designing them. Let's dive in. Today we will cover several crucial topics. First, we will explore the features of a good programming language. Then we will discuss the trade-offs involved in language design. We will also compare high-level and low-level languages. Lastly, we will take a look at some successful programming languages and analyze their design. A good programming language has several key features that contribute to its success. First, simplicity. It's important that a language is easy to learn and use. Second, expressiveness. Programmers should be able to clearly express their ideas without excessive boilerplate code. And finally, portability. Code should run on different platforms without significant changes. Apart from the basic features, a good programming language also needs to perform well. Performance is crucial, especially for applications that require a lot of computation. Readability and maintainability of code is another important feature. Developers should be able to understand and modify the code easily. Reusability promotes modularity, and finally, safety and security features help to prevent errors and vulnerabilities in the code. In the design of a programming language, there are always trade-offs. For example, performance often comes at the cost of ease of use. High-level languages are easier to work with but may be slower, while low-level languages offer more control and better performance but are harder to use. Similarly, flexibility and safety must also be balanced. Dynamic typing can be more flexible, but static typing offers better safety. Another important trade-off involves simplicity versus functionality. A language can be simple but lack advanced features, or it can be feature-rich but more complex. Additionally, when designing a new language, there's always the issue of backward compatibility. Sometimes sticking to older systems may limit innovation, but it's necessary for maintaining compatibility. Now let's look at the difference between high-level and low-level languages. High-level languages are designed to be closer to human language, making them easier to learn and use. Examples include Python and Java. They allow for faster development but often sacrifice execution speed compared to low-level languages. On the other hand, low-level languages such as assembly and C offer more control over hardware and resources. They enable faster execution but require more effort from the programmer. Low-level languages are more complex and harder to debug, but they are essential for system-level programming where performance is crucial. Let's now look at some successful programming languages. Python is a great example, known for its simplicity and readability. It has become a go-to language for web development, data science, and automation. C, being closer to hardware, excels in system programming and high-level performance applications. And Java, with its platform independence, is widely used in enterprise applications. Other notable languages include JavaScript, which powers most of the web with its event-driven nature. Rust has gained popularity due to its focus on safety and performance, particularly in systems programming. Lastly, Lisp, one of the oldest programming languages, is known for its flexibility and influence on functional programming. Let's dive into some case studies to understand the real-world impact of language design. Take C++ for example. It combines low-level control with high-level abstraction, making it powerful but complex language. The trade-off here is between performance and ease of use, with C++ offering fast execution but a steep learning curve. Go is another language designed for simplicity and efficiency, particularly in modern computing environments. It's easy to learn and works well for scalable applications. Haskell, on the other hand, is purely functional, with an emphasis on immutability and strong typing, offering benefits like fewer bugs but requiring a different mindset for developers. Now that we have covered the theory, let's put it into practice. In Activity 1, we will compare Python and C++ to understand their differences, the design decisions that make each language suitable for different types of projects. In Activity 2, we will discuss the trade-offs involved in designing a new programming language. Specifically, we will look at balancing safety and performance, an important consideration when choosing a language for a project. By the end of today's session, you should have a better understanding of the key considerations in designing a programming language. You will also appreciate the trade-offs involved and why certain languages succeed in specific contexts. In conclusion, the design of a programming language has a significant impact on its usability, performance, and suitability for different tasks. By understanding these design considerations, you will be better equipped to choose the right language for your projects and make informed decisions when working with various programming languages. Welcome to Day 6, Formal Languages and Automata Theory. In this session, we will explore formal languages, finite automata, context-free grammars, and push-down automata, which are foundational to computer science, especially in areas like compiler design, programming languages, and syntax analysis. Let's begin by understanding what formal languages are. A formal language is a set of strings formed from an alphabet and governed by specific rules or grammar. These languages are crucial because they provide the basis for designing programming languages, compilers, and interpreters. Formal languages are widely used in fields such as syntax analysis, pattern matching, and natural language processing, enabling computers to interpret and process structured data. Now let's dive into finite automata. Finite automata are computational models used to recognize regular languages. They are simple machines with a finite number of states that can process input symbols one by one to determine if the string belongs to a given language. There are two types of finite automata, deterministic and non-deterministic. A DFA has exactly one state transition for each input symbol, whereas an NFA can have multiple state transitions for the same input symbol. Let's consider an example of a DFA and NFA recognizing the string that end in 101. Next, we will discuss regular languages. These are languages recognized by finite automata. Regular languages have some important properties such as closure under operations like union, concatenation, and clean start, making them quite versatile. Regular expressions are a key tool for describing regular languages. They provide a convenient way to define patterns in text, and they are equivalent to finite automata in power. Moving to context-free grammars, a context-free grammar is a formal grammar used to describe the syntax of programming languages. It consists of non-terminals, terminals, a start symbol, and production rules that define how strings are generated. An example of a context-free grammar is one that defines simple arithmetic expressions such as expression assigned, expression plus term. These grammars are essential for the syntax analysis phase in compilers. Now let's explore pushdown automata. A pushdown automaton is an extension of finite automata that includes a stack. This allows it to recognize context-free languages, making it more powerful than finite automata. Pushdown automata are particularly useful for recognizing nested structures such as balanced parentheses in programming languages. This makes them ideal for parsing nested expressions. Formal languages have various practical applications. Finite automata are used in lexical analysis for tasks such as tokenization. For example, regular expressions can be used to validate email addresses or match URL patterns. Context-free grammars are commonly used in compilers to analyze the syntax of programming languages. Pushdown automata are particularly useful in parsing structures like nested parentheses in expressions. Let's look at some practical examples. A DFA can be used to recognize binary strings that end in 101. Similarly, a context-free grammar can be used to define arithmetic expressions like x plus y times z. Pushdown automata are well suited for recognizing balanced parentheses in strings like this. These practical examples illustrate the relevance of formal languages and automata theory in real-world computing. As we move to advanced topics, let's discuss the limitations of finite automata and pushdown automata. Finite automata cannot handle nested structures such as palindromes, and pushdown automata are limited to context-free languages which exclude certain complex structures. Turing machines extend beyond finite automata and pushdown automata. They are a theoretical model of computation that can simulate any algorithmic process, making them fundamental to the theory of computation. In this section, we will work on some hands-on activities. First, you can try writing regular expressions to validate email addresses. This will give you practical experience with pattern matching. Next, you can design a finite automata or NFA to recognize a specific string pattern or implement a context-free grammar to parse simple expressions. Lastly, simulate a pushdown automata to match balanced parentheses. To summarize, formal languages and automata theory are essential for understanding the fundamentals of programming languages and compilers. Finite automata, context-free grammars, and pushdown automata are tools that help us recognize and parse languages, which are crucial in computer science and software development. Thank you for joining today's session on formal languages and automata theory. I hope you now have a deeper understanding of these important concepts and their applications. Don't forget to explore the hands-on activities to strengthen your knowledge. Welcome to day 7 of our Principles of Programming Languages course. Today we will be diving into data types and type systems. Let's explore how different programming languages handle data and types, and the importance of understanding these concepts. In this session, we start by understanding what data types are and their significance. Data types determine the kind of data a variable can hold and are fundamental to how programs handle and store information. They play a crucial role in preventing errors and improving program efficiency. Data types can be categorized into primitive types and derived types. Primitive data types are the most basic types such as integers, floating point numbers, characters, and booleans. These types serve as the building block for all programming languages. Derived data types include arrays, lists, pointers, and strings. These types are built using primitive types and allow for more complex data structures. Abstract data types, ADTs like stacks, queues, maps, and sets offer even higher levels of abstraction. How is data represented at the machine level? At its core, data is stored in memory, and understanding the memory alignment and size considerations helps programmers optimize performance and avoid errors. Different languages may represent different in various ways, but the underlying principles are the same. Now let's talk about the type systems. A type system is a framework that defines how variables and expressions are assigned types and how these types affect program execution. It governs everything from memory allocation to error handling and performance. In programming, you often encounter strong and weak typing. Strong typing means that a variable is strictly enforced to hold a particular data type. For instance, in Java and Haskell, you cannot assign a string to an integer variable. This helps catch errors early in the development process. On the other hand, weak typing allows implicit type conversion. For example, in languages like JavaScript and PHP, you can assign a string to an integer variable, and the language will automatically convert it to the correct type. While this flexibility can be convenient, it may also lead to unexpected behavior and bugs. Now let's compare static and dynamic typing. Static typing, found in languages like C and Java, checks the type of variables at compile time. This means type errors are caught before the program runs, which can result in faster execution and fewer runtimes. Dynamic typing, as seen in languages like Python and Ruby, allows variables to change types at runtime. This adds flexibility and can make development faster, but it also introduces the possibility of runtime errors if types aren't handled properly. Type checking can happen either at compile time or runtime. Compile time checking ensures that type errors are caught early. On the other hand, runtime checking occurs when the program is executing. Both approaches have their pros and cons, depending on the language and use case. Type interface is a feature in many modern programming languages, where the compiler automatically deduces the type of a variable based on the value it's assigned. This can help reduce boilerplate code and make code more concise while still maintaining type safety. Nullable or optional types are a feature in languages like Kotlin and Swift, which allow a variable to be set to null or none explicitly. This reduces the risk of null pointer errors, which can crash applications if not handled properly. Enumerated types allow us to define a variable that can hold a specific set of values. For example, the days of the week or the states of a process. Enums provide better readability and prevent invalid values from being assigned. Pattern matching is a feature often used with enums, especially in languages like Rust and Haskell. It makes handling different variants of data easier and more expressive, leading to cleaner and more maintainable code. Polymorphic types such as generics allow a single function or data type to work with multiple types. This ensures type safety without sacrificing flexibility. Languages like Java and C# use generics extensively to allow developers to write reusable and type-safe code. Let's look at some real life examples. First, basic calculations with primitive types. For instance, you can perform arithmetic operations with integers or floating point numbers. These operations are essential in most programs. Data storage examples include using arrays or lists. For example, creating a list of student grades or managing shopping cart items. These data structures are fundamental in nearly all applications. In this section, we have some hands-on exercises. We will explore static versus dynamic typing, type interface in practice, and implement a generic container in languages like Java or C++. These exercises will help reinforce the concepts we have covered. To summarize, data types and type systems are essential for ensuring that your code is correct, efficient, and safe. We discussed the differences between strong and weak typing, static and dynamic typing, and how type checking, in- inference, and nullable types contribute to robust programming. That concludes today's session. Now I would like to open the floor for questions and discussion. Feel free to share your thoughts on how different type systems impact your experience with programming. Welcome to day 8 of our Principles of Programming Languages course. Today we will be exploring the concept of type safety and type checking. In this session, I will guide you through these important topics that ensure our programs run reliably and safely. Let's begin by defining what we mean by type safety. Type safety refers to ensuring that operations in a program are performed on compatible data types. In simpler terms, it prevents errors caused by mismatched data types, enhancing the robustness and reliability of the code. This is a crucial feature in many programming languages as it helps reduce runtime errors and maintain program correctness. Type safety is not just a theoretical concept, it's a practical necessity in modern programming. Some languages like Java and Python ensure a degree of type safety by enforcing rules about how types interact. Other languages like Haskell are known for their strong type systems which help prevent a wide range of bugs. Next, let's explore the difference between compile time and runtime type checking. In compile time checking, the compiler verifies that types are correct before the program runs. This helps check errors early in the development process. On the other hand, runtime type checking happens when the program is running. Errors are caught only when an operation is attempted on incompatible types. This type of checking allows for more flexibility as seen in dynamically typed languages like Python and JavaScript. However, it can lead to errors that are only detected when the code is executed, making debugging more challenging. Let's look at an example of type errors. In C++, if you try to assign a string value to an integer variable, the compiler will flag it as an error during the compilation process. For instance, declaring an integer and assigning it a string will result in a compilation error because the types are incompatible. In Python, This kind of error can occur at runtime. If you try to add a string to an integer, Python will throw a runtime error saying the operands are of incompatible types. These kinds of errors are harder to catch compared to compile time errors because they only show up during execution. Now let's talk about static versus dynamic type checking. Static type checking occurs at compile time, ensuring that type-related errors are caught before the program runs. In statically typed languages like C++ or Java, the compiler checks for type correctness during compilation, helping to prevent type mismatches. Dynamic type checking, however, happens during the program's execution. In dynamically typed languages such as Python or Java, you can change the type of a variable during runtime and the language will not enforce type checking until the operation is performed. This provides more flexibility but can result in runtime errors if types are mismatched. Type inference is another interesting feature that helps ensure type safety. It's the ability of a programming language to automatically deduce the type of a variable without needing explicit type annotations. For example, in C++, you can use the auto keyword and the compiler will infer the type of the variable based on its assigned values. In Python, the type is inferred at runtime. If you assign an integer to a variable, Python infers it as an integer. Later, if you assign a string to the same variable, it infers the type as a string. While this makes the code more flexible, it also requires careful attention to avoid type-related issues. There are several mechanisms to maintain type safety in programming languages. One of the most common is type annotations. Type annotations allow you to explicitly define the data types of variables or functions or function parameters. In Python, for example, you can annotate the types of function arguments to make the code easier to understand and debug. Another mechanism is strict type mode, which enforces the use of specific types. TypeScript is an example of a language that enforces strict typing, helping prevent issues that arise from dynamically typed languages. Additionally, some languages use runtime validators, which, which are libraries that check types during execution to ensure that type safety is maintained. Let's touch on some advanced topics in type safety. Subtyping is an important concept. It allows you to use a subtype where a subtype is expected, enabling more flexibility while still maintaining type safety. For example, a method that accepts an object of type shape can also accept objects of type circle or rectangle if they intend from the if they inherit from the shape class. Polymorphism is another key concept that can affect type safety. It ensures that different types can be handled in a uniform way without breaking the type rules. Lastly, generics and type constraints in languages like Java and C# allow you to create flexible yet type-safe code by restricting the types that can be used with generics. To summarize, type safety is a crucial concept that ensures operations are performed on the compatible data types, preventing errors in your program. Compile time and runtime type checking each have their benefits, and type inference, annotations, and strict typing help ensure that type safety is maintained. By understanding and applying these principles, you can write more reliable and bug-free code. Welcome to day 9 of our programming course. Today we will be learning about control structures. We will cover sequence, selection, and iteration in programming, as well as conditional statements, loops, and recursion. First, let's talk about sequence. Sequence refers to the execution of instructions in a linear order, one after the other. Each line of code is executed in the order it appears, which is the most straightforward way of structuring a program. For example, when you assign values to variables, they are processed sequentially. Like in this example, int x equals to 5, b int b equals to 10, and int c equals to a plus b. This is a simple sequential flow. Next, we have selection. Selection allows your program to make decisions based on certain conditions. In programming, we use conditional statements to select the path of execution. The most common ones are if, else, and switch statements. For example, in the if-else structure, if a condition is true, one set of actions will be executed, otherwise a different set of actions takes place. Here we check if a number is greater than 0 using an if-else statement. If true, the program prints positive number, otherwise it prints non-positive number or negative number. Now let's look at iteration or loops. Iteration allows us to repeat a set of instructions until a certain condition is met. This is useful when we don't know the exact number of times an action needs to be performed. There are several types of loops in programming. The for loop is typically used when the number of iterations is known. The while loop checks the condition before every iteration. Finally, the do while loop ensures that the code is executed at least once before checking the condition. All of these help in repeating actions efficiently. Conditional statements are essential in controlling the flow of the program. These statements help us choose between different actions based on conditions. For example, the if-else structure allows us to check a condition and based on whether it's true or false, execute one of two possible code blocks. In this example, we are checking if a number is greater than 10. If true, we print greater than 10. Otherwise, we print less than or equal to 10. Now let's dive into recursion. Recursion occurs when a function calls itself to solve a smaller instance of the problem. Recursion consists of two parts, the base case and the recursive cases. The base case defines when the recursion should stop, and the recursive case calls the function again with a modified input. For example, in a factorial function, we keep calling the function with smaller numbers until we reach the base case, where n equals 0. So why is recursion important? Recursion simplifies complex problems by breaking them down into smaller, more manageable subproblems. It allows for elegant solutions, especially when dealing with problems like sorting, searching, or traversing hierarchical data structures like trees. For example, the Fibonacci sequence is a great example of recursion. By defining the problem in terms of smaller instance, we can calculate Fibonacci numbers efficiently. To recap what we have covered today, sequence refers to the execution of statements in a linear, step-by-step manner. Selection involves making decisions based on conditions using if, else, or switch statements. Iteration allows us to repeat code using loops like for, while, or do while. Recursion solves problems by calling functions within themselves, breaking problems into smaller parts. These control structures are the building blocks of any program, allowing us to write efficient and logical code. Welcome to Day 10, Variables and Memory Management. In this session, we will explore key concepts around variables, memory management, and the differences between stack and heap memory, as well as how memory allocation works in programming. To begin, let's understand what variables and memory are in programming. A variable is a named storage location in memory that holds a value. The type of data it holds is defined by its data type, such as an integer or a float. Memory, on the other hand, is where all your data and program instructions are stored while a program is running. Managing memory efficiently is critical for the performance and stability of software. Now let's look at stack memory. Stack memory is used for static memory allocation, meaning it's used to store local variables and function calls. Memory is allocated and deallocated automatically as functions are called and returned. It's fast to access, but it has a limited size. Once a function call completes its memory, it's cleared from the stack. Next, we have heap memory. Heap memory is used for dynamic memory allocation, which allows you to allocate memory for objects and large data structures during runtime. This memory is slower to access compared to stack memory, but it has a much larger size. Memory allocation on the heap persists even after a function call returns, unlike stack memory. To summarize the differences between stack and heap memory, stack memory is used for storing local variables and function calls with automatic memory management. If it offers fast access but limited size. Heap memory, on the other hand, is used for dynamic memory allocation, and while it's larger, it requires manual and or automatic management. The key difference is that stack memory is automatically managed, while heap memory requires more control from the programmer. There are two primary types of memory allocation: automatic and manual. Automatic memory allocation is managed by the compiler or runtime environment, such as with local variables and function calls. Manual memory allocation requires the programmer to explicitly allocate and deallocate memory, as seen in languages like C++ with functions such as malloc and free. Manual memory management provides more control but also adds complexity. Now let's talk about garbage collection versus manual memory management. Garbage collection is an automatic process in languages like Java and C Sharp where memory that is no longer in use is freed up automatically. While this simplifies the programmer's job, it can also add runtime overload. In contrast, manual memory management gives the programmer full control but requires careful tracking of memory usage to avoid memory leaks and errors. Memory management comes with its challenges. One common issue is memory leaks, which occur when memory is allocated but not properly deallocated, leading to wasted memory. Another issue is dangling pointers, which happen when a pointer still references a memory location that has been freed. Lastly, memory fragmentation can occur when memory is allocated and deallocated frequently in small chunks, making the available memory less efficient. So, how can we manage memory more effectively? For automatic memory management, consider using garbage collected languages when performance isn't the highest priority. For manual memory management, it's important to use memory profilers and tools to analyze memory usage. In languages like C++, smart pointers like std shared ptr can reduce memory management errors, and it's always important to regularly review your code to ensure memory is properly deallocated. To wrap up, we have covered key concepts of stack and heap memory, as well as the differences between automatic and manual memory management. Effective memory management is crucial for preventing errors like memory leaks and dangling pointers, ensuring that your programs run efficiently and without crashes. Both stack and heap memory serve different purposes, and understanding their differences will help you write better, more efficient code. That concludes today's session on variables and memory management. If you have any questions or need further clarification, feel free to ask now. I am happy to discuss any points in more details. Welcome to today's presentation on functions and procedures in programming. In this session, we will explore key concepts that help in writing modular and reusable code. A function is a block of code that performs a specific task and can be reused multiple times in a program. Functions help in breaking down complex problems into smaller, manageable parts. They allow us to write more readable, maintainable, and modular code. Here's how we define and call a function. To define a function, we specify its return type, name, and the parameters it takes. For example, the function add takes two integers and returns their sum. When calling the function, we simply pass the required arguments like in add 3, 4 and get the result. In programming, we can pass arguments to the two functions in two primary ways, by value and by reference. When passing by value, a copy of the argument is made, so changes inside the function does not affect the original value. On the other hand, passing by reference allows the function to modify the original argument directly. Recursion is when a function calls itself in order to solve smaller subproblems. A recursive function has two parts, a base case which stops the recursion and the recursive case where the function calls itself. For example, a factorial function calls itself repeatedly until it reaches the base case. Recursion is important because it simplifies solving problems that have repetitive, self-similar patterns. Problems like sorting, searching, and traversing trees can often be solved more elegantly using with recursion. However, care must be taken with recursion as it can lead to performance issues like stack overflow if not managed properly. Closures are functions that remember the environment in which they were created, allowing them to access variables from their surrounding scope. High order functions, on the other hand, are functions that take other functions as arguments or return functions as results. These concepts make your code more flexible and allow for advanced programming techniques. Functions can return different types of values such as integers, floats, or even objects. Function overloading allows us to define multiple functions with the same name but different parameter types. This helps in writing cleaner code when we have similar operations for different types of inputs. Lambda functions are anonymous functions typically written in a single line of code. They allow for concise and functional programming, often used as arguments for higher order functions. In Python, for example, a lambda function can quickly perform operations without requiring a full function definition. When it comes to function scopes, there are local and global scopes. Variables defined inside a function are local, meaning they are only accessible within that function. Global variables, however, can be accessed from anywhere in the program. Understanding scope and lifetime is essential for managing variable access and preventing errors. When solving problems, we often have the choice between recursion and iteration. Recursion can be elegant and simplify the solution for certain problems, but it may lead to issues like stack overflow. Iteration, on the other hand, can be more efficient for tasks that don't naturally fit into a recursive pattern. To summarize, functions allow us to modularize and reuse code. Recursion helps us solve problems by calling functions within themselves. Higher order functions and closures make our code more flexible and concise. Lastly, understanding scopes, return types, and function overloading are essential for writing efficient and maintainable code. Thank you for your attention. Now let's open the floor to any questions or discussions on the topics we have covered today. Feel free to ask about real-world applications of functions, recursion, or any other programming concepts. Hello and welcome to this presentation on Object-Oriented Programming or OOP. Today we will explore key OOP concepts including classes, objects, inheritance, polymorphism, and design principles that are essential for creating modular, maintainable, and efficient software. Object-oriented programming is a programming paradigm that revolves around objects. These objects contain data and methods that operate on that data. OOP promotes better organization of software and allows for easier maintenance and modification. The key benefits of OOP include abstraction, encapsulation, inheritance, and polymorphism. At the core of OOP are classes and objects. A class acts as a blueprint for creating objects which are instances of that class. For example, imagine a class car with attributes like brand and year, and a method start that defines how the car starts. Objects are the actual instances, like my car, that use these attributes and methods to perform operations. Inheritance is one of the key features of OOP. It allows one class to inherit properties and methods from another class, promoting code reuse. For instance, if you have a class electric car that inherits from the class car, the electric car will automatically have all the properties of car plus additional features like battery life and charge method. Polymorphism allows us to treat objects of different classes as objects of a common base class. This is achieved through method overloading and overriding. Overloading happens at compile time while overriding occurs at runtime. For example, in method overloading, we can have multiple methods with the same name but different parameters. In method overriding, a subclass provides a specific implementation of a method defined in a superclass. Let's now look at the four fundamental principles of OOP: abstraction, encapsulation, inheritance, and polymorphism. Abstraction hides the complex implementation details and shows only the essential features, while encapsulation bundles data and methods, protecting the object's internal state. These principles work together to make software easier to understand and maintain. Design patterns are proven solutions to common problems in software design. They offer best practices for solving recurring issues and improving software flexibility and maintainability. Some popular design patterns include the singleton, factory, and observer patterns. These patterns can help make our software more modular and acceptable to changes. SOLID is an acronym for 5 principles that guide object-oriented design. These principles, single responsibility, open-closed, Leskov substitution, interface segregation, and dependency inversion, ensure that software is easier to maintain, test, and scale. By adhering to solid principles, we can build software that is both efficient and robust. Let's consider a real-world example of inheritance and polymorphism. We can create a class vehicle with a move method. Then we define two subclasses, car and bike, that each override the move method to provide specific functionality. This demonstrates how polymorphism allows us to treat different types of vehicles as a common vehicle object while each performs its own action. In summary, object-oriented programming helps us break down complex systems into manageable parts by using key concepts like classes, inheritance, polymorphism, and principles like solid. We can create software that is modular, scalable, and easy to maintain. Design patterns further help in solving common design issues, improving code quality and flexibility. Thank you for your attention. Now I will be happy to take any questions you might have. Feel free to ask about any aspect of object-oriented programming, whether it's about specific concepts, examples, or how to apply these principles in real-world projects. Welcome to this presentation on functional programming concepts. In this session, we will explore key ideas such as immutability, pure functions, higher order functions, and more. Let's dive into the core concepts of functional programming. Functional programming focuses on several key concepts. First, immutability means that once a value is assigned to a variable, it cannot be changed. Second, pure functions are those that always return the same output for the same input with no side effects. Next, we have higher order functions, which takes other functions as arguments or return them as results. And finally, referential transparency, which allows us to replace an expression with its value without changing the program's behavior. Immutability is a cornerstone of functional programming. Once a variable is assigned a value, it cannot be modified. This reduces side effects, making the code easier to reason about. Immutability also enhances concurrency safety, as there are no shared mutable states that can lead to unexpected results. Next, we will discuss pure functions. A pure function's output depends solely on its input values with no side effects. This makes pure functions highly predictable, easier to test and debug. An example of a pure function is a simple addition function, where the result is always determined by the inputs and no external states are modified. Functional programming treats functions as first-class citizens. This means that they can be assigned to variables, passed as arguments, and returned as results. Higher order functions are a key feature as they take other functions as inputs or return them as outputs. For example, the map function can apply a given operation to each element in a list. Lambda expressions are anonymous functions defined inline. These allow us to define small functions on the fly, making code concise and readable. For instance, a lambda expression is in Haskell can be used to multiply every element of a list by 2, simplifying the operation. Lazy evaluation is a strategy where expressions are only evaluated when their values are needed. They can lead to significant performance gains, especially in large datasets. It also allows us to work with infinite data structures where the elements are computed only when required. In functional programming, recursion replaces loops as the primary way to iterate. Recursive functions call themselves with modified parameters to solve a problem. For example, calculating the factorial of a number can be done through recursion, where the function calls itself with a reduced values. Here's an example of recursion in Haskell. This function SumList recursively sums the elements of a list by adding the first element to the sum of the rest of the list. The base case is an empty list where the sum is 0. Libs is another language known for functional programming. In libs, we can define functions like the factorial function using recursion. This highlights lib's powerful support for symbolic computation and functional programming. Let's compare functional programming to imperative programming. In functional programming, we focus on what we want to compute, while in imperative programming, we focus on how to perform the computation. Functional programming avoids mutable state and side effects, whereas imperative programming typically uses loops and changes states. Functional programming offers several key benefits. Modularity, since functions can be reused throughout the program. Predictability, as pure functions are easy to test. And concurrency, since immutability always allows for safer multi-threaded programming. However, functional programming also comes with challenges. There's a learning curve when transition from imperative to functional programming. Recursion and immutability can introduce performance overhead, and functional programming languages have more limited adoption in some industries. To conclude, functional programming emphasizes immutability, pure functions, and higher order functions, offering benefits like modularity, predictability, and concurrency safety. However, it may also present challenges such as performance and learning curve. That wraps up the presentation. If you have any questions, feel free to ask now. I would be happy to clarify any concepts. Welcome to day 14, Logical Programming. In this session, we will explore the key concepts and applications of logic programming, a declarative programming paradigm based on formal logic. Let's dive into this fascinating topic. Logic programming is a programming paradigm where we express facts and rules about a problem domain, and the system reduces answers through logical inference. Unlike imperative programming, where we focus on how to do something, logic programming is about what to do. It allows us to describe problems in a more natural, declarative way. Let's explore the key concepts in logic programming. First, we have facts, which are basic statements about the world. For example, John loves Mary. Next, we have rules, which allow us to infer new facts from existing ones. An example of a rule could be, if John loves someone and that person loves Mary, then John loves that person. Finally, we have queries, which are how we ask the system to deduce solutions or verify facts. Prolog is one of the most widely used languages for logic programming. In Prolog, facts are written as simple statements like loves John, Mary. Rules are defined with a head and a body, and queries ask the system whether something is true. For example, we can ask Prolog, does John love Mary? And Prolog will check the facts to answer. Rule-based systems are a core component of logic programming. These systems make decisions based on a set of rules which follow an if-then structure. For example, in a medical expert system, a rule might state if a person is sick and has fever, they should see a doctor. Rule-based systems are used in applications such as expert systems and decision support systems. One of the fundamental techniques in logic programming is backtracking. This technique helps the system explore multiple possibilities to find a solution. If one possibility fails, the system backtracks and tries another path. For instance, when Prolog tries to answer a query, it may need to backtrack to explore all possible solutions. Unification is another key concept in logic programming. It is the process of making two terms identical by finding a suitable substitution for variables. For example, in the fact loves John, X, Prolog will attempt to unify X with Mary if the fact loves John, Mary exists in the knowledge base. Unification is what allows Prolog to match facts and rules to provide answers. Let's look at an example in Prolog. Consider the following facts: Father Abraham, Isaac, Father Abraham, Isaac, Jacob, and Father Jacob, Joseph. We have a rule for grandfather, grandfather X, Y, Father X, Z, Father Z, Y. When we ask Prolog grandfather Abraham, X, it uses backtracking and unification to find all possible solutions. Prolog will deduce that Abraham is a grandfather to both Jacob and Joseph. Logic programming is widely used in various fields. In expert systems, it helps simulate human expertise by encoding knowledge in rules. In natural language processing (NLP), logic programming can be used to represent the syntactic structure of sentences. It also employed in artificial intelligence, where reasoning and decision making are central, as well as in constraint logic programming, which solves complex problems like scheduling and optimization. To summarize, logic programming is a powerful paradigm focused on formal logic and deduction. Prolog is a popular language used for this purpose. With its reliance on facts, rules, queries, backtracking, and unification, this paradigm has many applications, including expert systems, NLP, and AI, and it provides a unique way to solve problems. That concludes our overview of logic programming. Do you have any questions or comments? Let's open the floor for discussion. Welcome to this presentation on declarative versus imperative languages, where we will explore two fundamental programming paradigms. In this presentation, we will go through key concepts, differences, and examples to understand when and why each paradigm is used. Let's begin with a quick overview of what we will be covering. Our objective today is to understand the differences between declarative and imperative programming. We will also explore real-world examples and use cases for each paradigm to help you understand how they shape the way we write code. Imperative programming focuses on how a task is performed using a sequence of statements. In this paradigm, you tell the computer exactly what steps to take to achieve a specific outcome. It emphasizes control flow and changes to program states. Common imperative languages include C, C++, Java, and Python. Declarative programming, on the other hand, focuses on what the program should accomplish rather than how to achieve it. In this paradigm, you describe the desired outcome and the system or framework handles the execution details. Languages like SQL, HTML, Haskell, and Prolog are declarative in nature. Now, let's compare the key differences between two paradigms. Imperative programming requires you to specify how to perform each step, while declarative programming focuses on what needs to be done. In imperative programming, control flow and state changes are explicitly defined, whereas in declarative programming, these are abstracted away. Here's an example of imperative programming in Python. In this example, we explicitly define the steps to sum a list of numbers by iterating over each element and updating the total sum. This shows how imperative programming focuses on describing the sequence of operations required to achieve the result. Now let's look at an example of declarative programming in SQL. Here, instead of specifying how to iterate through the numbers, we simply ask the system to give us the sum of the numbers. The system decides how to compute the sum, allowing us to focus on what we need, not the implementing details. Imperative programming is ideal for tasks that require fine-grained control over the execution. It's commonly used in system-level programming, game development, and performance-critical applications where the programmer needs to control exactly how operations are performed. Declarative programming, on the other hand, is best suited for tasks that focus on outcomes rather than the process of achieving them. For example, database queries, web page markup, and logic-based tasks benefit from declarative programming. It abstracts away much of the complexity, making the code easier to maintain and understand. Some advantages of imperative programming include the ability to optimize performance and have fine-grained control over the system. However, these advantages come at a cost. Imperative code can become complex and harder to maintain, especially in large systems. Declarative programming offers a simple, more abstracted approach. It, it's easier to read and maintain since the focus is on the end goal rather than the process. However, this approach may lead to less control over the execution and in some cases can be less efficient for complex tasks. Many modern programming languages combine both paradigms to offer flexibility. For instance, in Python, we can write declarative SQL queries within the program, and in frameworks like React, we use declarative UI components but may write imperative logic to manage data and events. This hybrid approach allows us to get the best of both worlds. In conclusion, understanding the distinction between declarative and imperative programming is essential for choosing the right paradigm for a task. While imperative programming provides more control over execution, declarative programming allows for cleaner, more maintainable code. Modern languages often blend both paradigms to suit different needs. Thank you for your attention. Now I'd be happy to answer any questions you may have. Welcome to this presentation on memory management techniques. Today we will explore topics like stack versus heap allocation, memory leak detection, manual versus automatic garbage collection, and case studies comparing C++ and Java. Let's start with an overview of what we will cover in this session. We will dive into stack versus heap allocation, the techniques to detect memory leaks, the differences between manual and automatic garbage collection, and conclude with some case studies comparing C++ and Java. First, let's talk about stack memory. Stack memory is used for temporary storage of local variables and function calls. It follows a LIFO last in first out structure. The memory is automatically freed when variables go out of scope, but it has limitations. The most notable limitation is that it has a fixed size, and if that size exceeded, a stack overflow occurs. Next, we have heap memory, which is dynamically allocated at runtime. It allows more flexible memory management but comes with its own trade-offs. Memory is allocated manually, and if not properly deallocated, it can lead to memory fragmentation. Unlike stack memory, heap memory needs to be manually freed by the programmer, which can sometimes be error prone. Now let's look at memory leak detection. A memory leak occurs when memory that is no longer needed isn't freed, causing wasted memory and reducing system performance. Common causes include failure to deallocate dynamically allocated memory and circular references, especially in garbage collected languages. Tools like Valgrind, Address Sanitizer, and Static Code Analyzer can help detect and prevent memory leaks. Moving on to manual memory management, in languages like C and C++, the programmer is responsible for both allocating and deallocating memory. While this offers fine-grained control over memory, it also increases the risk of errors such as memory leaks and segmentation faults. Manual memory management requires careful tracking of every allocation and deallocation. On the other hand, automatic garbage collection, like in Java, takes over the task of memory deallocation, freeing up memory when objects are no longer in use. While this reduces the burden on the programmer and helps prevent memory leaks, it introduces some challenges such as performance overhead and potential pauses in program execution during collection cycles. Let's now look at C++, which uses manual memory management. Memory is allocated using new and freed with delete. However, if we forget to call delete, the allocated memory will not be released, resulting in a memory leak. Tools like Valgrind can detect these leaks using smart pointers like std unique ptr or std shared ptr is a safer approach as they automatically manage memory. Next, let's examine Java. In Java, the JVM handles memory management with automatic garbage collection. The garbage collector takes care of freeing memory when objects are no longer in use. However, there are different types of garbage collection, including minor GS for young objects and major GS for older objects. With this simplifies memory management, While this simplifies memory management, it can introduce performance overhead, especially in memory intensive applications. Now let's talk about some best practices for memory management. In manual memory management, it's crucial to always free dynamically allocated memory using delete or equivalent functions. Smart pointers in C++ help reduce the risk of memory leaks. RAII resource acquisition is initialization is another important principle, ensuring that resources are automatically cleaned up when they go out of scope. For automatic garbage collection, best practices include minimizing object creation in critical loops to reduce GC impact and using weak references to avoid unnecessary retention of objects. Optimizing memory use in long-running applications will also help improve performance and reduce garbage collection cycles. In conclusion, manual memory management provides control but comes with the risk of errors like memory leaks. On the other hand, automatic garbage collections simplifies memory management but at the cost of performance overhead. Regardless of the approach, tools and best practices can help optimize memory management and reduce potential issues. Thank you for your attention. Welcome to today's lesson on abstraction in programming languages. In this presentation, we will cover data abstraction, function abstraction, encapsulation, and polymorphism, all of which are essential concepts in object-oriented programming. Let's start with an overview of abstraction. Abstraction is the process of simplifying complex systems by focusing on the essential details while hiding unnecessary information. The main goal of abstraction is to reduce complexity, making it easier to understand and work with software systems. Data abstraction is about hiding the implementation details of data structures and exposing only the necessary aspects. For instance, in C++, we can use abstract classes to define a common interface for different data types, while the underlying details remain hidden. This allows us to interact with objects in a simplified manner without needing to understand the internal workings. Function abstraction follows a similar principle but focuses on functions or methods. We hide the complexity of the function's implementation, presenting only the interface that users need to interact with. For example, Python's built-in sum function allows us to add numbers without worrying about how the function processes them internally. Encapsulation is the practice of bundling data and methods that operate on that data into a single unit or class. This not only improves organization but also restricts access to the data, preventing unintended manipulation. In Java, we achieve this by making data fields private and providing public methods to access and modify them, ensuring that data is accessed in a controlled manner. Information hiding is an integral part of encapsulation. It involves restricting access to certain details of an object and only exposing the necessary parts. For example, in Java, we make fields private and provide public getter and setter methods, which ensures that external code cannot directly alter the object's internal state. Polymorphism in object-oriented programming allows objects of different types to respond to the same method call in their own unique way. This makes our code more flexible and reusable. Polymorphism comes in two forms: method overloading, where multiple methods share the same name but differ in parameters, and method overriding, where a subclass provides its own version of a method defined in the superclass. Abstraction and polymorphism go hand in hand in object-oriented programming. Abstraction hides the implementation details, while polymorphism allows different objects to respond to the same interface in different ways. This combination makes our code more adaptable and maintainable. We, as we can add new objects or modify existing ones without changing the interface that other parts of the system rely on. Now let's look at the key benefits of abstraction. First, it simplifies the design by hiding unnecessary details. It also makes our code more maintainable as internal changes don't affect the user interface. Abstraction promotes code reusability, allowing us to use common operations across different parts of our system, and increases flexibility by enabling us to evolve the system without breaking existing functionality. To summarize, abstraction helps manage complexity by hiding irrelevant details and focusing on the essential. Data and function abstraction simplify the way we handle data and operations, while encapsulation protects data. Polymorphism makes our code more flexible and reusable, and all these concepts are fundamental in object-oriented programming, leading to modular, maintainable systems. That concludes the presentation. Do you have any questions or would you like further clarification on any of the concepts we discussed today? Hello and welcome to the presentation on error handling mechanisms in programming. In this session, we will explore types of errors, exceptions, and how error recovery works in programming languages like Java, Python, and C++. Let's dive in. Error handling is a crucial aspect of any programming language. It allows developers to anticipate and manage issues that may arise during the execution of their code. In this presentation, we will focus on different types of errors, how exceptions are handled, and how to propagate and recover from errors. We will look at examples in Java, Python, and C++. Errors can be categorized into three main types: syntax errors, runtime errors, and logical errors. Syntax errors occur when the code does not follow the correct language rules, such as missing semicolons or misspelled keywords. These errors prevent the program from compiling. Runtime errors occur during the program's execution, like division by zero or null pointer exceptions. These errors cause the program to crash if not handled properly. Finally, logical errors do not stop the program but result in incorrect behavior, like producing wrong output due to a flawed algorithm or condition. Exceptions are used to handle runtime errors in a more structured way. When an error occurs, an exception is thrown and the program can catch it and respond appropriately. In Java, for example, we would use a try-catch block to catch exceptions. The try block contains the code that may cause an exception, and the catch block handles it. This ensures that your program continues running smoothly even if an error occurs. Sometimes you need to ensure that certain code is executed regardless of whether an exception occurs or not. This is where the finally block comes in. It is used for cleanup actions like closing files or releasing resources. Even if an exception is thrown, the finally block will execute, ensuring proper resource management. In some cases, you may want to handle different types of exceptions in one block. You can do this by catching multiple exceptions using separate except clauses or a single except clause with multiple exception types. This approach makes your error handling more concise and organized. Error propagation refers to how an exception moves up the call stack when it is not caught at the current level. It continues to propagate until it is either caught or reaches the top of the stack, causing the program to terminate. Error recovery is a mechanism through which the program can continue running after an error. This can involve retrying operations, using fallback strategies, or presenting meaningful error messages to the user. Let's look at an example in Java. If we try to open a file that does not exist, a file not found exception will be thrown. We handle this by using a try catch block. In the catch block, we can print a message to inform the user that about the missing file, ensuring the program does not crash. In Python, error handling is very similar. We can catch exceptions like value error or zero division error using multiple except blocks. This allows us to handle different types of exceptions in a structured way, making our code more resilient to errors. In C++, exception handling works with try-catch blocks as well. If an error is encountered, such as trying to divide by 0, an exception can be thrown. We catch the exception in the catch block and display an appropriate message to the user. This prevents the program from crashing unexpectedly. In conclusion, error handling is an essential practice in software development. It not only helps catch and fix errors, but also ensures that your application runs smoothly even when something goes wrong. By using exceptions, try-catch blocks, and other mechanisms, developers can create more robust and user-friendly applications. Thank you for your attention. Now I would like to open the floor for any questions you might have. Feel free to ask anything about error handling, exceptions, or any of the concepts discussed today. Welcome to this presentation on concurrency and parallelism in programming languages. Today we will explore the concepts of concurrency, threads, processes, and how different programming languages implement these principles. Let's dive in. Concurrency refers to the ability of a program to manage multiple tasks at the same time, even though they might not be executed simultaneously. The key benefit of concurrency is resource management. For example, handling multiple file downloads concurrently increases efficiency and responsiveness in applications. Let's start with the distinction between threads and processes. A thread is the smallest unit of execution within a process. Threads within the same process share memory space and resources. In Java, we can create a thread using the thread class and start it with the start method. On the other hand, a process is an independent unit of execution with its own memory space. In C++, we can create a process using the fork function. Unlike threads, processes do not share memory, making them more isolated but heavier on system resources. So, what's the key difference between threads and processes? Threads share memory and resources, which allows for faster context switching. Processes, however, have their own independent memory space, making them more resource intensive. Threads are ideal for lightweight tasks, while processes are best suited for tasks that require isolation. Java supports concurrency through its built-in multithreading capabilities. The thread class and the runnable interface allow us to create threads. We can override the run method in the thread class to define the task and then start the thread with the class method. Java also provides thread synchronization mechanisms, ensuring that shared resources are accessed safely. The synchronize keyword helps to prevent race conditions. ensuring only one thread accesses a resource at a time. In Go, concurrency is built into the language using Go routines. A Go routine is a lightweight thread managed by the Go runtime. Go routines are created using the Go keyword and they can be executed concurrently with other tasks. Go also uses channels for synchronization and communication between coroutines. Channels also allow Go routines to send and receive data safely, making it easier to coordinate and synchronize concurrent tasks. Synchronization ensures that multiple threads or processes access shared resources without conflicts. This can be done using mechanisms like locks. In Python, for example, we can use the threading lock to ensure that only one thread modifies a resource at a time. Deadlock occurs when two or more threads or processes are waiting for each other to release resources, creating a standstill. This can be avoided through careful resource allocation strategies or using timeouts to prevent indefinite waiting. Parallelism refers to executing multiple tasks simultaneously, often used often using multiple processors or cores. This is particularly useful for computationally intense tasks as it reduces execution time by dividing the workload across multiple units. While concurrency involves logically managing multiple tasks, parallelism focuses on performing tasks simultaneously. Concurrency handles tasks in a way that might appear to be happening at the same time, but not necessarily. Parallelism, on the other hand, executes tasks at the same time on separate processors. In Python, we can implement concurrency using the asyncio library. This allows us to define tasks that can run concurrently by utilizing asynchronous programming. For example, we can run multiple tasks concurrently with the await keyword, managing their execution efficiently. To achieve parallelism in Python, we can use the multiprocessing library. This allows us to run tasks in parallel on different CPU cores, making it ideal for CPU-bound tasks. Each process runs independently with its own memory space, improving performance for heavy computations. To sum up, both concurrency and parallelism are crucial concepts for developing efficient applications. Concurrency helps in managing multiple tasks, while parallelism speeds up computationally heavy operations. Understanding these concepts and how they are implemented in different programming languages will help you optimize your code. That concludes the presentation on concurrency and parallelism. Thank you for your attention. If you have any questions or need further clarification, feel free to ask. Welcome to day 20 of our programming languages series. Today we will dive into the implementation of programming languages covering essential phases like lexical analysis, parsing, and code generation. We will also explore the differences between compilers and interpreters and learn how just-in-time compilation works. Let's start with lexical analysis, the first phase of language implementation. This step breaks down the source code into meaningful units called tokens. These tokens include keywords, operators, and identifiers. Lexical analyzers such as lex or flex are used to perform this task, ensuring that the code is ready for the next phase. After lexical analysis, we move on to parsing. Here the tokens are arranged in a structured format like a parse tree or an abstract syntax tree or AST. Parsing ensures that the sequence of tokens follows the grammar rules of the language, setting the foundation for further analysis and code generation. Once parsing is completed, we proceed to semantic analysis. This phase checks for logical errors such as type mismatch or improper use of variables. The code is then ready for code generation, where it is transformed into machine or intermediate code. The code generation process turns the structured representation into executable code. Now let's compare compilers and interpreters. The compiler translates the entire source code into machine code at once, generating an executable file. Like languages like C and C++ uses compiler. On the other hand, an interpreter processes the code line by line, executing it immediately. Examples of interpreted languages include Python and Ruby. Compilers are known for their speed. Once the code is compiled, it runs faster than interpreted code because it has been converted to machine code ahead of time. Additionally, compilers can optimize the code for better performance. However, they do require time to compile the source code before execution. On the flip side, compilers have some drawbacks. The main disadvantage is the long compilation time, especially for large code bases. Additionally, compiled code must be recompiled for each platform, limiting probability. Interpreters, by contrast, don't require a separate compilation phase. Code is executed line by line directly from the source. This gives interpreters flexibility and debugging is easier since you can track errors as they occur. However, interpreters generally have slower execution speeds due to the line by line translation. While interpreters offer flexibility, they also have significant downsides. The primary issue is slower execution speed, as the code must be interpreted each time it runs. Moreover, because there's no separate executable, the source code must be present to execute the program. Now let's talk about just-in-time JIT compilation. JIT compilation combines the best of both worlds. The code is compiled during runtime, allowing for optimizations based on how the code is actually being used. Java is a prime example of a language that uses JIT. The code is first compiled into bytecode and then optimized and executed by the Java Virtual Machine or JVM. In practice, different languages implement these strategies in various ways. For example, Java uses JIT compilation, while Python is interpreted but also utilizes bytecode for performance. C++ is typically compiled directly into machine code. Understanding these implementation strategies can help you choose the right language for your needs. Why does all this matter? Language implementation strategies directly affect performance, debugging, and portability. Compiled languages tend to offer faster execution but may be less flexible, while interpreted languages are easier to debug but slower. Understanding these differences can help you choose the best language for your project. To recap, language implementation involves several phases: lexical analysis, parsing, semantic analysis, and code generation. Understanding how compilers and interpreters work helps in choosing the right language for specific tasks. JIT compilation offers a balance of speed and flexibility, and different languages implement these strategies in various ways. Welcome to the presentation on runtime systems. Today we will explore concepts such as stack and heap management, virtual machines like JVM and CLR, and garbage collection strategies. Let's dive in. Here's the agenda for today's session. We will start by discussing stack and heap management, followed by virtual machines, specifically the JVM and CLR. Finally, we will look at garbage collection strategies and their importance in memory management. First, let's talk about stack and heap management. The stack is used to store local variables, function parameters, and return addresses. It operates on a last in first out or LIFO principle, meaning the most recently used items are processed first. It's fast and automatically managed by limited in size. On the other hand, the heap is used for dynamic memory allocation, and memory is managed at runtime. It provides more flexibility but can introduce overhead due to the need for manual or automatic memory management, depending on the programming language. Let's take a look at some examples. For the stack, when a function is called, its local variables and parameters are pushed onto the stack. When the function finishes, the stack is popped, removing those items. In the heap, we have dynamic memory allocation. For example, in C++, we use the new and delete operators, while in Java, the new keyword allocates memory on the heap, and garbage collection handles memory management. Now let's explore virtual machines, starting with the Java Virtual Machine or JVM. The JVM abstracts the underlying hardware and operating system, providing a consistent environment for running Java programs. It executes bytecode and performs just-in-time compilation, converting bytecode into machine code at runtime. The Common Language Runtime or CLR is part of .NET framework. It manages the execution of .NET programs, supports cheat compilation, and provides garbage collection, ensuring efficient memory management. The JVM has several key components. The class loader loads class files into the JVM at runtime. The bytecode interpreter executes Java bytecode, ensuring cross-platform compatibility, and the garbage collector automatically reclaims memory, preventing memory leaks by cleaning up unused objects. Similarly, the CLR provides key features for .NET applications. It handles garbage collection, automatically reclaiming unused memory. It also compiles Common Intermediate Language or CIL into machine code through JIT compilation. Additionally, the CLR enables interoperability with unmanaged code such as calling C or C++ libraries from managed code. Garbage collection is a crucial part of memory management. It automatically reclaims memory that is no longer in use, helping prevent memory leaks and improving. Welcome to today's presentation on day 22, Abstract Machines in Programming Languages. In this session, we will explore the fundamental concepts of Turing machines, abstract machines, and how they apply to language design and implementation. Let's begin by defining abstract machines. These are simplified computational models that represent the behavior of a program. Their primary purpose is to bridge the gap between high-level programming language constructs and the underlying machine execution. This makes it easier to understand how a program runs at a machine level. Turing machines are a key concept in the theory of computation. A Turing machine consists of several components: a tape, a head, a finite state machine, and a transition function. The tape is an infinite memory that holds input data. The head reads and writes on the tape, and the transition functions determines how the machine moves between states based on input symbols. This simple yet powerful model can simulate any computational process. Turing machines are foundational to understanding computability. They give us the concept of Turing completeness, which refers to the ability of a system to perform any computation that can be described algorithmically. This concept helps define the limits of what can and cannot be computed, laying the groundwork for language theory and the development of programming languages. Now let's explore the role of abstract machines in language design. Abstract machines serve as models for how a program is executed on a machine. They simplify complex computations, focusing on key aspects such as memory management and execution order. These abstract models influence the design and implementation of programming languages, including systems like the Java Virtual Machine (JVM) and Python Virtual Machine (PVM). Abstract machines play a crucial role in interpreters and compilers. In an interpreter, high-level code is executed directly using the abstract machine with no compilation step. For instance, Python uses the Python virtual machine to run code. On the other hand, compilers translate high-level code into intermediate or machine code, using abstract machines to represent the execution model. A notable example is the JVM, which compiles Java bytecode into machine-readable instructions. Abstract machines also help optimize the execution of programs. During the compilation process, abstract machines allow us to model aspects like memory usage and control flow, which helps identify optimization opportunities. Just-in-time JIT compilation is a key optimization strategy, where intermediate code is dynamically compiled into native machine code at runtime, improving performance. Let's look at some real-world examples of abstract machines. The Java Virtual Machine or JVM executes Java bytecode, allowing Java programs to run on any platform. The .NET Common Language Runtime (CLR) performs a similar function for .NET languages, managing memory, garbage collection, and security. JavaScript engines like V8 and SpiderMonkey also rely on abstract machines to interpret and optimize JavaScript code. Performance optimization is another important role of abstract machines. With JIT compilation, abstract machines focus on frequently executed parts of code, compiling them to native machine code during runtime for improved performance. Additionally, abstract machines handle memory management such as garbage collection to ensure efficient use of system resources and prevent memory leaks. To summarize, Turing machines lay the foundation for our understanding of computation and language theory. Abstract machines help simplify the execution model of high-level programming languages, making it easier to implement interpreters, compilers, and virtual machines. They also enable optimizations like JIT compilation and garbage collection, enhancing performance and resource management. Thank you for your attention. Now I would like to open the floor for any questions or discussions. Feel free to ask about any aspects of abstract machines, their roles in language design, or how they influence modern programming practices. Welcome to this presentation on scripting languages. Today we will explore their characteristics, applications, and limitations. Let's dive in. Scripting languages are high-level, interpreted programming languages. They are known for their ease of use, rapid development cycle, and platform independence. In this section, we will cover the key characteristics of scripting languages, such as being interpreted, dynamically typed, and their ability to integrate easily with other languages. Scripting languages are interpreted, meaning the code is executed directly by an interpreter at runtime, rather than being compiled. They are dynamically typed, which means the variable types are determined while the program runs. Additionally, scripting languages have a simpler syntax, allowing for quicker development and testing. These languages are also platform independent, meaning they can run on different operating systems without modifications. Lastly, they offer excellent integration with other programming languages, making them versatile. Some popular scripting languages include Python, known for its simplicity and versatility in areas like web development, data science, and automation. JavaScript is essential for client-side web scripting, providing interactivity on a web page. Ruby is another powerful language often used for web development with frameworks like Ruby on Rails. We also have Bash for Unix-based system scripting and Perl, which excels in text processing and system administration. Scripting languages have a wide array of applications. In web development, Python is used for server-side scripting, while JavaScript powers the client side. They are also great for automation tasks, simplifying system configuration and deployment. Data analysis and processing are areas where Python, Ruby, and Perl shine. Scripting is also utilized in game development for handling game mechanics, and system administration tasks are often automated through bash scripting. While scripting languages have many advantages, they do come with certain limitations. One of the main drawbacks is performance. Since they are interpreted, scripting languages typically run slower compared to compiled languages. Additionally, concurrency support can be limited, making it challenging to handle multi-threading or parallelism. Memory management, especially with garbage collection, can also introduce performance issues. These languages are not suitable for low-level operations like direct hardware manipulation, and they require an interpreter to run, creating a dependency on specific platforms. Scripting languages offer several advantages. They are perfect for rapid prototyping, allowing developers to quickly develop and test ideas. The concise code with reduced boilerplate makes development faster. These languages are cross-platform, meaning they can run on various operating systems without changes to the code base. Additionally, scripting languages have a rich ecosystem of libraries and frameworks, which further accelerates development. The future of scripting languages looks promising. They are integrated, increasingly integrated with emerging technologies such as machine learning, artificial intelligence, and cloud computing. Python in particular is gaining momentum in the data science field with advancements in just-in-time compilation and other optimization techniques. The performance gap between scripting and compiled languages is closing. Furthermore, the flexibility of using multiple languages in a single project makes scripting languages an attractive option for developers. In conclusion, scripting languages play a crucial role in modern software development. They offer speed and flexibility, making them ideal for tasks like web development, automation, and data analysis. However, it's important to be mindful of their limitations, particularly in terms of performance and concurrency. By understanding both their strengths and weaknesses, we can leverage scripting languages effectively. That wraps up the presentation. Now I would be happy to answer any questions you may have. Feel free to ask about anything we have covered or additional insights you would like to explore. Hello and welcome to this presentation on domain-specific languages, DSLs. In this presentation, we will explore DSLs, their types, key characteristics, advantages, challenges, and real-world applications. Let's dive in. First, let's start with an introduction to domain-specific languages. A domain-specific language or DSL is designed to solve problems in a specific domain. Unlike general-purpose programming languages, DSLs offer specialized syntax and semantics tailored to specific tasks, making them more efficient to domain-specific problems. DSLs are highly specialized, whereas general-purpose languages like Python or Java are versatile but not as efficient for specific tasks. DSLs have several key characteristics. They are specialized for a specific domain, which means they are designed to solve domain-specific problems. Their syntax is tailored to make those tasks easier and more intuitive. DSLs are also highly expressive, allowing developers to write less code for complex tasks. Overall, they provide efficiency and reduce the development effort for specific problems. Now let's discuss the two main types of DSLs, internal DSLs and external DSLs. Internal DSLs are embedded within a general purpose programming language, extending the existing syntax and capabilities of that language. Examples include Ruby on Rails and LinkU in C Sharp. External DSLs, on the other hand, are standalone languages with their own syntax and semantics, such as SQL, regular expressions, and HTML. Internal DSLs or embedded DSLs are built within general-purpose languages. They leverage the existing features of the host language, extending it for domain-specific purposes. These DSLs don't exist as independent languages, but instead they provide specialized syntax within the general-purpose language. Some well-known examples of internal DSLs include Ruby on Rails, a web development framework that provides a DSL for web development tasks. LinkU is another example in C Sharp, providing a specialized syntax for querying collections. RSpec in Ruby is also an internal DSL for behavior-driven development testing. These examples show how internal DSLs can simplify complex tasks within the domain. Internal DSLs offer several advantages. They integrate well with existing code bases, allowing developers to take advantage of the general purpose language features. Developers are also familiar with the host language, reducing the learning curve. However, there are challenges. Internal DSLs may not offer the same level of optimization as external DSLs. and their expressiveness can be limited compared to standalone DSLs. Now let's look at external DSLs. These are standalone languages designed for specific tasks. Unlike internal DSLs, they do not depend on a general purpose language. They have their own custom syntax and parsing rules, making them highly specialized for particular domains. Examples of external DSLs include SQL, a language used for managing and querying relational databases, regular expressions, which are used for string pattern matching, and HTML, a powerful language for structuring content on the web. These DSLs are independent and offer powerful domain-specific capabilities. External DSLs come with their own set of advantages. They provide highly specialized syntax that simplifies complex domain tasks, and they allow developers to express ideas concisely. However, they also come with challenges, such as steep learning curve since developers need to learn the unique syntax. Additionally, integrating external DSLs with other systems may require custom parsers, adding complexity. To give you better understanding of how DSLs are used, let's look at some examples. SQL is widely used for database queries, regular expressions are used for pattern matching in text, and HTML structures web pages. These languages are designed to solve specific problems in their respective domains, making them highly effective tools. Here are few more examples. LaTeX is a powerful typesetting language used for scientific and academic documents, while CSS is used to style web pages. These DSLs demonstrate how specialized syntax can make domain-specific tasks easier and more efficient. DSLs have various applications across different industries. In web development, frameworks like Ruby on Rails and Django use internal DSLs. In database management, SQL is the go-to DSL. Regular expressions are used in text processing, and LaTeX is commonly used in scientific computing for typesetting research papers. These are just a few examples of how DSLs are leveraged in real-world applications. Using DSLs brings several benefits. They increase productivity by simplifying complex tasks, improve readability by providing a clear and concise syntax for specific domains, and make code more efficient. DSLs are a powerful tool in the hands of developers when used for the right tasks. Despite their advantages, DSLs also have challenges. The learning curve can be steep due to the unique syntax and semantics of the language. Integrating DSLs with other systems, especially external DSLs, can be tricky and may require additional tools or custom parsers. Additionally, DSLs are specialized, which means they may not be useful outside their specific domain. In conclusion, domain-specific languages offer a powerful way to tackle specialized problems. They simplify complex tasks, improve productivity, and offer concise and effective code. While they have limitations, understanding how and when to use DSLs can greatly enhance your work in specific fields like web development, database management, and scientific computing. Thank you for your attention. Now I would be happy to take any questions you might have. Welcome to today's presentation on programming paradigms. In this section, we will explore the core concepts of programming paradigms and their impact on software development. Programming paradigms refer to the different approaches or styles of programming. They shape the way we solve problems and structure code. Understanding these paradigms is essential because they help us choose the right approach for a given task, improving both productivity and maintainability. Let's dive into the key paradigms in programming. There are five main paradigms we will cover today: procedural, object oriented, functional, logic, and concurrent programming. Each of these paradigms offer unique ways to approach problem solving, and we will look at each of them in more detail shortly. Procedural programming is one of the oldest paradigms, focusing on a sequence of instructions or steps to solve a problem. It's centered around functions or procedures that process data, often using loops and conditionals. Popular languages like C, Pascal, and Fortran use this approach. A classic example is calculating a factorial through a series of procedural steps. Object-oriented programming, or OOP, is based on modeling real-world entities as objects with properties and behaviors. The key principles of OOP are encapsulation, inheritance, polymorphism, and abstraction. Languages like Java, C++, and Python use OOP. A great example is a class hierarchy where a vehicle can be subclassed into cars, trucks, or electric vehicles. Functional programming treats computation as the evolution of mathematical functions, avoiding changing state or mutable data. It's built around functions that take inputs and produce outputs without side effects. This paradigm emphasizes immutability, first-class functions, and pure functions. Languages like languages such as Haskell, Scala, and Python support functional programming. We often see examples like map and reduce being used to manipulate data. Logic programming is a paradigm based on formal logic. It uses facts, rules, and queries to solve problems. Instead of specifying how to solve a problem, you define relationships and let the system infer the solution. Prolog is the most well-known language for this paradigm. For example, you might define relationships like father, John, Mary, and ask queries such as who is the father of Mary. Concurrent programming focuses on managing multiple tasks simultaneously. This paradigm is crucial for real-time systems, multi-core processors, and handling multiple users. Concurrency involves synchronizing threads or tasks to avoid conflicts and ensure smooth execution. Languages like Java, Python, and Go provide features for concurrency such as threads and coroutines. Each paradigm has its strengths depending on the task at hand. Procedural programming works well for straightforward, sequential tasks. OOP excels in scenarios requiring complex systems of interacting entities. Functional programming is ideal for tasks requiring immutability and mathematical computations. Logic programming is best suited for tasks involving reasoning, while concurrent programming is essential for real-time and multi-threaded applications. Let's consider the example of building a simple calculator in different paradigms. In procedural programming, we would write a sequence of steps for each calculation. In OOP, we could define classes for functions, for numbers and operations. In functional programming, we might use functions like map or reduce. In logic programming, we would define rules for operations and query the system for results. Finally, in concurrent programming, we could handle multiple calculations at once using threads. To conclude, each programming paradigm has its own strengths and ideal use cases. Understanding these paradigms allow developers to choose the right tool for the task, improving efficiency and software quality. Whether you are working with simple scripts or complex systems, the right paradigm can make all the differences. That wraps up the presentation. I would now like to open the floor for any questions or further discussion. Feel free to ask about any of the paradigms or examples we have discussed today. Thank you for your time and attention. If you have any additional questions or need further clarification, don't hesitate to reach out. I appreciate your participation and hope you find this session informative. Welcome to the presentation on the evolution of programming languages. In this session, we will explore the historical development of programming languages and key milestones that shaped the way we code today. Programming languages have evolved to meet the demands of different computing domains. From early languages like Fortran and COBOL to modern languages such as Python and Rust, the landscape of programming has been shaped by the needs of developers and the advancements of technology. Today, we will dive into these key milestones and understand their impact on software development. We begin with the early programming languages. In 1957, Fortran or formula translation became the first high-level language designed for scientific and engineering computations. It introduced key concepts such as loops, conditionals, and arrays, laying the foundation for many languages to follow. Similarly, COBOL, developed in 1959, was created for business applications. Its English-like syntax made it more readable even for those without a technical background, and it became widely used in government and financial sectors, still present in legacy systems today. In 1972, C was developed by Dennis Ritchie. It was a breakthrough for system programming, and its low-level memory access made it highly efficient for performance-critical applications. C became the language of choice for operating systems like Unix. Building upon C, C++ was introduced in 1983 by bringing object-oriented programming features like classes, inheritance, and polymorphism. C++ allowed developers to write both efficient system-level code and high-level applications, making it popular for games and graphics programming. In 1995, Java was born. Java's "write once, run anywhere" philosophy revolutionized portability with the help of the Java Virtual Machine or JVM. This allowed Java applications to run on any platform without modification, making it a dominant force in enterprise, web, and mobile applications. Java's robust and secure nature helped it establish a strong presence in web applications and Android development. With its widespread use in enterprise systems, Java's impact on software development is undeniable. As we move into the modern era, Python emerged in 1991, designed by Guido van Rossum with a focus on simplicity and readability. Python's versatility made it a favorite for beginners and experts alike, allowing it to thrive in web development, data analysis, and machine learning. Go, created by Google in 2009, emphasized simplicity and concurrency. With support for lightweight concurrent programming through Go routines, Go became ideal for building scalable cloud applications and microservices, particularly in large distributed systems. Meanwhile, Rust, developed by Mozilla in 2015, offered a solution to memory safety without sacrificing performance. Its innovative features like ownership and borrowing made it an attractive choice for system-level programming and high-performance applications with a focus on safety and concurrency. To summarize, the evolution of programming languages is driven by the specific needs of developers and the changing landscape of technology. Early languages like Fortran and COBOL served scientific and business purposes, while languages like C, C++, and Java introduced powerful paradigms like object-oriented programming and platform independence. Modern languages like Python, Go, and Rust now focus on readability, performance, and safety. The evolution of programming languages continue to shape the future of software development. By understanding this history, developers can make more informed decisions about which language to use for specific tasks, ensuring that their software is built for efficiency, scalability, and maintainability. Thank you for your attention. Now I would be happy to answer any questions you may have. Feel free to ask anything related to the evolution of programming languages or the concept we have covered today. Welcome to this presentation on the comparative study of programming languages including C, C++, Java, Python, and JavaScript. In this presentation, we will explore their strengths, weaknesses, performance, usability, and more. Let's dive right in. Programming languages are the foundation of software development. Today, we will focus on five popular languages: C, C++, Java, Python, and JavaScript. We will cover their histories, key features, and the factors to consider when choosing the right language for your project, including performance, readability, and usability. Let's begin by comparing these languages based on their general characteristics and typical use cases. C is a procedural language mainly used in system programming and embedded systems. C++ is an extension of C supporting object-oriented programming and is often used in game development and systems programming. Java is an object-oriented language known for its portability, used in enterprise applications, mobile apps like Android, and large-scale systems. Python is a high-level language prized for its simple syntax and widely used in web development, data science, and machine learning. JavaScript is primarily used for web development, both for front-end and back-end applications using frameworks like Node.js. Now let's look at performance. C and C++ offer the highest performance since they are low-level and give developers direct memory control. They are ideal for applications that require high efficiency, such as system programming or games. Java is slower compared to C, C++ due to its reliance on Java Virtual Machine, which interprets bytecode. However, its platform independence and automatic garbage collection make it suitable for large-scale enterprise applications. Python tends to be slower because of its interpreted nature and dynamic typing, but its ease of use makes it great for rapid development and prototyping. JavaScript has relatively good performance in web applications thanks to modern just-in-time compilers in browsers, though it's not as fast as C, C++ for complex non-web tasks. Next, let's discuss readability. C and C++ can be more challenging for beginners due to their complex syntax and advanced features such as pointers and manual memory management. Java is readable, though its verbosity can sometimes make the code harder to maintain. Python is widely praised for its clean, simple syntax. It focuses on readability and uses indentation to define code blocks, making it an excellent choice for beginners. JavaScript is more flexible but has a history of inconsistent syntax, which can be confusing, especially with modern updates. like ES6 and beyond. Let's now quickly at let's now look at usability. C is ideal for low-level programming such as operating systems and embedded systems, where performance is critical. C++ is versatile, used in both low and high-level applications. It's commonly found in game development, simulations, and applications that require high performance. Java shines in large-scale, enterprise-level applications and cross-platform development. It's also used in Android development. Python is great for rapid development, making it perfect for web development, data science, machine learning, and automation. JavaScript is essential for web development, enabling interactive websites and full-stack applications. Choosing the right language depends on your project's needs. If performance is your top priority, C or C++ should be your go-to languages. If you need cross-platform compatibility, Java or Python may be better suited for your project. For rapid development or when prototyping, Python and JavaScript are often the best choices due to their ease of use. If you are building a large-scale, long-term system, languages like Java or C++ are better for maintainability and scalability. In conclusion, the best programming language for your project depends on several factors, including performance, platform requirements, speed of development, and long-term maintainability. Understanding the strengths and weaknesses of each language will help you choose the right tool for your needs. Always consider your project's goals and requirements when selecting a language. That concludes the presentation. Thank you for your attention. Now I would be happy to answer any questions you might have. Welcome to the presentation on language and compiler design. In this session, we will explore the inner workings of compilers, how they transform high-level code into machine-readable instructions, and how various optimization techniques enhance the efficiency of generated code. Let's begin with an overview of compiler design. A compiler is a program that converts high-level source code into machine-level code that can be executed by a computer. It plays a crucial role in making code portable across different platforms. The design of a compiler ensures that the code is transformed accurately while also optimizing its performance and resource usage for efficient execution. Compilers operate in multiple phases, each responsible for a specific task in the code transformation process. The first phase, lexical analysis, breaks the code into smaller units called tokens. In the syntax analysis phase, the compiler checks the code for grammatical correctness and generates an abstract syntax tree or AST. Next, semantic analysis ensures that the code is logically correct, followed by intermediate code generation, which prepares the code for further transformation. Code optimization enhances performance by eliminating redundancies and inefficiencies. Then code generation converts the code into machine or assembly language. And finally, code emission outputs the executable code. Lexical analysis is the first step in the compilation process. In this phase, the compiler breaks the source code into tokens such as keywords, operators, and identifiers. For example, the statement int a equals to 5 would be broken down into tokens int a equals to 5 and semicolon. Tools like lex and flex are often used to generate lexical analyzers automatically. Syntax analysis follows lexical analysis and ensures that the structure of the code adheres to the grammar rules of the language. During this phase, the compiler parses the tokens and creates a syntax tree. For example, the statement int x equals to 5 would be represented as an assignment in the tree syntax with int a equals and 5 as its component. In the code generation phase, the compiler takes the abstract syntax tree from the syntax analysis phase and converts it into machine or assembly code that the computer can understand and execute. For instance, the high-level statement int a equals to 5 would be translated into assembly instructions specific to the target machine architecture. Optimization is an important phase in compiler design. The goal of optimization is to improve the performance of the code without changing its functionality. This includes techniques like roll, loop unrolling, constant folding, dead code elimination, and register allocation. These optimizations reduce redundant computations and improve the efficiency of the code at runtime. Let's look at an example of optimization. Before optimization, the code int x equals to 2 plus 3 requires the compiler to calculate the sum each time the program runs. After optimization, the expression is simplified to x int x equals to 5 during compilation, eliminating unnecessary computation during runtime. This small optimization improves program performance. Now it's time for a practical exercise. Your task is to write a simple lexical analyzer for a basic programming language subset. The analyzer should recognize basic contrasts such as keywords, operators, and identifiers. You can use tools like lex or flex to automate this process. Next, we will implement a syntax parser. In this exercise, you will create a parser for simple arithmetic expressions such as a plus b times c. The goal is to generate a syntax tree that visually represents the structure of the expression. In the third exercise, we will apply basic optimization techniques such as constant folding and loop unrolling to improve code performance. By comparing the performance before and after optimization, you will be able to see the tangible benefits of these techniques. There are several tools and frameworks available for compiler design. Lex and Flex are popular tools for lexical analysis. For parsing, we have tools like Yak and Bison. Compiler frameworks like LLVM and GCC offer powerful infrastructure for building efficient compilers. If you want to dive deeper into compiler constructions, Compilers, Principal Techniques and Tools by Aho, Lane, Sethi, and Ullman is a great resource. In conclusion, understanding compiler design is essential for anyone working with programming languages. It allows you to see how high-level code is translated into machine instructions and how optimizations can enhance program performance. In the next step, I encourage you to explore compiler construction in more depth and experiment with designing your own compilers and optimizations. Thank you for your attention. If you have any questions or would like to discuss any concepts further, feel free to ask now. I am happy to dive deeper into any topics related to compiler design. Welcome to day 29, Static versus Dynamic Scoping. In this session, we will explore the rules of scoping, compare static and dynamic scoping, and dive into real-world examples in programming languages. Let's start by understanding what scoping is. Scope defines the region in a program where a variable can be accessed. It governs the visibility and lifetime of variables, helping avoid naming conflicts in the code. Understanding scoping is crucial for writing clean and maintainable code. Now let's look at the two primary types of scoping, static and dynamic. In static scoping, the scope is determined by the structure of the source code and is resolved at compile time. In dynamic scoping, however, the scope is determined at runtime based on the execution call stack. Both approaches have their pros and cons, which we will discuss next. Static scoping, also known as lexical scoping, determines variable binding based on the program's source code structure. This means that when a variable is referenced, the compiler will resolve it by looking at the position of that variable in the code. Let's look at an example from C. Here we define a global variable x and a local variable x within function 1. The local variable shadows the global one within function 1, but outside of it, the global variable x is used. On the other hand, dynamic scoping determines variable binding based on the execution call stack at runtime. This means the value of a variable is resolved based on which function is currently executing. For instance, in libs, the variable x takes the value defined in the most recent function in the call stack, making it dynamic. This can sometimes result in unpredictable behavior, but it offers flexibility in certain use cases. Now let's compare static and dynamic scoping. In static scoping, the variable binding is resolved at compile time, making it easier to predict and debug. Static scoping is more commonly used in modern programming languages. On the other hand, dynamic scoping resolves variable binding at runtime, which can lead to unexpected results and harder debugging. Dynamic scoping offers flexibility but requires more careful management. Most modern programming languages such as C, C++, Python, Java, and JavaScript use static scoping due to its predictability and ease of use. However, languages like libs and Perl allow for scoping, providing more flexibility, especially in specific scenarios. Understanding the scoping rules of the language you are working with is essential for writing effective code. Scoping plays a significant role in debugging, performance, and readability. With static scoping, it's easier to track where variables come from and to ensure that their values are predictable. It also allows for better optimizations during compilation. Dynamic scoping can lead to unexpected results, making it harder to debug and optimize the code. It's important to consider the impact of scoping rules when designing your programs. So, when you should use static or dynamic scoping? Static scoping is generally preferred for large, complex systems because it offers predictability, easier debugging, and better performance. Dynamic scoping can be useful in smaller, flexible systems or in specialized languages where you need more dynamic behavior. Each approach has its place depending on the specific needs of the project. To summarize, static and dynamic scoping are two different ways of managing variable binding in programming languages. Static scoping is more common and predictable, making it easier to understand and debug. Dynamic scoping, while more flexible, can sometimes lead to unexpected behaviors which can complicate debugging. Choosing the right scoping model depends on your project requirements and the language you are using. Welcome to day 30 of our programming course. In today's session, we will be exploring paradigm-specific language constructs, focusing on how different programming paradigms introduce unique constructs that help developers solve problems in various ways. Programming paradigms introduce specific contrasts that shape how developers approach coding challenges. Each paradigm brings its own set of tools and techniques for solving problems, making it essential to understand these contrasts in order to choose the best approach for a given task. Let's start with functional programming. One of its key features is first-class functions, where functions are treated as first-class citizens. This allows us to pass functions as arguments, return them from other functions, and assign them to variables. Another important construct is map and reduce, which allows us to operate on collections of data. We have we also have lazy evaluation, where expressions are evaluated only when needed, and pure functions, which are functions that have no side effects and always return the same output for the same input. First-class functions allow us to pass functions around just like any other variable. For example, in Haskell, we can define an add function and then pass this function to another function that applies it to a list of numbers. This makes our code modular and more reusable. Map and reduce are higher order functions that are commonly used in functional programming. Map applies a function to each element in a collection, while reduce combines all the elements of a collection into a single value. For instance, in Python, we can use map to double each element in a list and reduce to sum all elements in a list. Lazy evaluation is another powerful concept in functional programming. It means that an expression is not evaluated until its value is needed. This allows us to work with infinite data structures or rely computation or delay computation until absolutely necessary. In Haskell, we can define an infinite list and take only the first few elements without causing any performance issues. Next, let's look at object-oriented programming, OOP. OOP introduces constructs like classes and objects, which acts as blueprints for creating instances of objects. Inheritance allows one class to inherit properties and methods from another, while polymorphism enables different classes to respond to the same method in different ways. Encapsulation protects an object's internal state by only exposing relevant information. In OOP, we define classes that serve as blueprints for creating objects. For example, in Python, we can define a class car with properties like model and methods like drive. We can then create an instance of the class like myCar equals to car Tesla and call its methods like mycar.drive to perform actions. Inheritance allows one class to inherit the functionality of another, while polymorphism lets us use the same method name for different types of objects. For instance, we might have a shape class with a method area and then circle and square classes that implements the area method in their own way. Polymorphism allows us to call area on both objects even though their implementations are different. Logic programming is based on facts and rules. It defines relationships between different entities and allows us to make logical deductions. For example, in Prolog, we define facts like parent Alice, Bob, and then use rules to deduce relationships like ancestors x, y, parent x, y, which means that x is an ancestor of y if x is a parent of y. Concurrent programming deals with multiple tasks running in parallel. Key constructs include threads, which are independent execution units, and synchronization primitives like locks and semaphores to manage concurrent access to shared resources. Message passing allows processes to communicate with each other as seen in languages like Erlang. In concurrent programming, we use threads to execute tasks independently. For instance, in Python, we can create a thread to print numbers concurrently with other tasks. Synchronization primitives like locks are used to ensure that threads do not interfere with each other when accessing shared data. Message passing is another critical feature in concurrent programming. It enables processes to communicate with each other by sending messages. For example, in Erlang, we can send messages between processes to coordinate their actions. This approach is especially useful in distributed systems. In conclusion, each programming paradigm offers specific contrasts that shape how we write and structure code. By understanding these constructs, such as first-class functions in functional programming, inheritance in OOP, and message passing in concurrent programming, we can make better decisions when choosing the right paradigm and tools for a task. Thank you for your attention. I would now like to open the floor for any questions or further discussions on paradigm-specific language constructs. Feel free to share your thoughts or ask for clarification on any topic we covered today. Welcome to the presentation on software design and language impact. Today we will explore how different programming languages influence software design, architecture, and overall development. In software development, the choice of programming language plays a significant role in shaping the design and functionality of a system. For example, languages with static typing such as Java or C++ encourage well-defined architecture and help catch errors at compile time. On the other hand, dynamic typing languages like Python and Ruby prioritize flexibility and fast development, but at the cost of potentially more runtime errors. Similarly, languages like C and C++ offer manual memory management, giving developers greater control, whereas languages like Java or Python handle memory management automatically through garbage collections, simplifying development but adding some performance overhead. When it comes to concurrency, languages like Go and Rust have built-in support for handling multiple tasks simultaneously, while others like Python rely on external libraries to manage concurrency. Different languages of software have different needs, and language choice is critical. For system software like operating systems and device drivers, languages like C and C++ are preferred due to their low-level capabilities and control over hardware. For enterprise applications that require scalability and robustness, Java is a popular choice due to its portability and strong typing. When it comes to web development, JavaScript dominates the front end, and with Node.js it also powers the backend. Python and Ruby are also widely used for web applications due to their simplicity and extensive frameworks. In data science and machine learning, Python has become the go-to language because of its rich ecosystem of libraries like TensorFlow and Pandas. For embedded systems where performance and direct hardware interaction are crucial, C and C++ continue to be the dominant choices. Design patterns, which are reusable solutions to common design problems, are influenced by the features of the programming language. Object-oriented languages like Java, C++, and Python encourage patterns like singleton, factory, and observer thanks to their support for classes, inheritance, and polymorphism. In functional programming languages like Haskell or Lisp, patterns like MapReduce are more prevalent as these languages emphasize immutability and the use of higher order functions. Modern concurrency languages like Go make use of patterns like the Ocar pool and publisher subscriber to manage multiple tasks concurrently using lightweight Go routines and channels. Object-oriented programming languages are built around the concepts of objects, classes, inheritance, and polymorphism. One common design pattern in OOP is the factory pattern, which is used to create objects in a flexible manner without specifying the exact class of the object to be created. This is particularly useful in Java, where object creation is often abstracted through interfaces and factory methods to promote loose coupling and easier testing. Functional programming focuses on immutability and the use of pure functions. The MapReduce pattern, popularized in languages like Haskell, Lisp, and Python, is a prime example of functional programming in action. It involves applying a function to each element of a collection, then reducing the result to a single value, such as the sum or average. This pattern is particularly effective in processing large datasets in parallel, which is why it is commonly used in distributed systems like Hadoop. Concurrency is a key consideration in modern software design, especially in high-performance systems. Languages like Go have built-in concurrency support through Go routines and channels, making it easy to implement patterns like publisher subscriber and worker pool. These patterns allow multiple tasks to be performed in parallel, improving the efficiency and responsiveness of applications, especially in systems handling many simultaneous connections such as web servers. Maintaining and extending software systems requires careful consideration of the language features. Readable and modular languages like Python make it easier to manage and update code over time. With strong community support and well-documented libraries, developers can easily extend functionality without breaking existing features. Flexible languages like Python and Ruby also allow easy integration of new modules or third-party libraries, making them ideal for rapidly evolving projects. When selecting a programming language, developers must weigh performance against productivity. High-performance languages like C and C++ provide fine-grained control over memory and processing but require more effort to handle memory management and concurrency. In contrast, languages like Python and Ruby emphasize rapid development, allowing developers to quickly prototype and iterate through though a potential sacrifice in performance. Additionally, long-term maintainability should be considered, with languages like Java and C# offering strong ecosystem support for enterprise applications, and Rust providing long-term safety for system-level development. To summarize, the choice of programming language profoundly affects software design, maintenance, and extensibility. By understanding the strengths and limitations of various languages, developers can make informed decisions that ensure the success of their projects. Thank you for your time and feel free to reach out if you have any questions or need further clarifications. Welcome to day 32 of our course, where we explore the advanced features of modern programming languages. Today we will be discussing coroutines, async, await, metaprogramming, reflection, and introspection, some of the most powerful tools available in modern languages to enhance performance, readability, and flexibility in your code. Let's start with coroutines, async, await, and concurrency. Coroutines allow functions to pause and resume execution without blocking threads. This is especially useful for tasks like I/O operations, networking, or event-driven programming. In languages like Python, Kotlin, C Sharp, and JavaScript, coroutines help manage asynchronous tasks without needing to deal with complicated callback mechanisms. Async await is a feature that simplifies asynchronous programming. It makes the code more readable and avoids the complexity of callbacks by allowing developers to write asynchronous code in a synchronous manner. And when we talk about concurrency, we are referring to the ability to execute multiple tasks simultaneously. This allows for more efficient use of system resources and better performance. Go's coroutines and Python's Essentio are great examples of concurrency in action. Concurrency is a key feature of modern programming languages. It involves executing tasks concurrently without blocking the main program execution. While concurrency does not necessarily mean parallel execution, it allows multiple tasks to progress independently, which helps with resource utilization and performance. Languages like Go with its lightweight Go routines and Python with which uses Asyncio for asynchronous tasks provide tools to implement concurrency effectively. It's a critical feature for large-scale applications that require responsiveness and efficient resource management. Now let's dive into metaprogramming. This is a powerful feature where the code can manipulate other code at runtime or even generate new code. There are two main types of metaprogramming: compile time and runtime. At compile time, metaprogramming allows for the creation of templates or generic code. For example, in C++, templates lets you write code that works for any data type. At runtime, languages like Python and Ruby allow for more dynamic code manipulation, such as creating new classes or methods. The key benefit of metaprogramming is the increased flexibility it provides. It can write less boilerplate code and make your programs more adaptable. Metaprogramming is widely used in frameworks and libraries to adapt code dynamically based on the user's need. For instance, in Ruby on Rails, metaprogramming is used to build domain-specific languages (DSLs), which are mini languages for specific tasks, making the code cleaner and more readable. Another application of metaprogramming is in code generation, where parts of the program can be created dynamically based on the environment or user inputs. This reduces the need for repetitive code, making the development process more efficient. Let's move on to reflection and introspection. Reflection is the ability of a program to inspect and modify its own structure at runtime. It allows developers to dynamically load classes, methods, and attributes. Introspection, a related concept, focuses on examining the properties of an object. For example, in Python, the dir function can be used to inspect an object's attributes and methods. These features are often used in frameworks that need to adjust their behavior dynamically based on the objects they are working with. Next, we have type interference. which allows programming languages to automatically deduce the type of a variable based on its assigned value. Languages like Kotlin, TypeScript, and Rust all use type inference to make the code cleaner and less verbose. For example, Kotlin allows you to declare a variable without specifying its type, and it will infer the correct type based on the assigned value. This not only reduces redundancy but also improves code readability. Pattern matching is another advanced feature that allows you to match values against patterns or types. It makes conditional logic more expensive and readable. In languages like Python, JavaScript, and Scala, pattern matching provides a more intuitive way to handle complex conditions. For instance, Python's match statement, introduced in version 3.10, allows you to match variables against patterns directly, making code much more elegant compared to traditional if-else or switch statements. Let's talk about memory management, particularly in languages like Rust. Rust is known for its unique approach to memory management, which does not rely on garbage collection. Instead, it uses ownership, borrowing, and lifetimes to ensure memory safety at compile time. This approach prevents common issues like memory leaks and race conditions, ensuring that developers can write high-performance applications without worrying about manual memory management. However, it does require more careful programming, making it more challenging for developers new to the language. With these advanced features like coroutines, metaprogramming, and memory management offer significant benefits that are trade-offs. The primary advantage is that these features allow for more efficient, flexible, and readable code. However, they can also increase complexity and introduce performance overhead, such as with reflection or dynamic typing. Moreover, some of these features, like Rust's memory management model, have a steeper learning curve. Developers need to balance the use of these features based on the specific requirements of their projects. In conclusion, modern programming languages provide a wide array of advanced features that can drastically improve the quality and performance of your code. From coroutines and async/await for concurrency to metaprogramming and reflection for dynamic behavior, these tools give developers a high degree of flexibility and control over their programs. Mastering these features will enable you to write more efficient, scalable, and maintainable software. However, it's important to understand when and how to use them to avoid overcomplicating your code. Thank you for joining me today. I hope you have a deeper understanding of advanced programming features like coroutines, metaprogrammings, and reflection. If you have any questions or would like to dive deeper into any topic, feel free to reach out. See you in the next session. Welcome to today's presentation on optimization techniques in programming languages. We will explore the key strategies for improving memory usage, performance, and the role of compiler optimizations in various programming languages. Let's dive into these crucial techniques. Optimization is an essential aspect of software development. In this section, we will discuss the different types of optimization techniques: memory optimization, performance optimization, and compiler optimizations. Additionally, we will look at language-specific optimization strategies and the role of profiling and benchmarking in identifying bottlenecks in your code. Code optimization varies across different programming languages. For example, in low-level languages like C and C++, manual memory management can significantly enhance performance. On the other hand, languages like Java rely on just-in-time compilation and automatic garbage collection. Python and JavaScript focus on profiling, list comprehensions, and optimizing asynchronous tasks. Understanding how optimization works in different languages helps you select the best approach for a specific application. Memory optimization is a critical aspect of performance, especially in resource-constrained environments. Different languages provide different memory management techniques. For instance, languages like Java and Python have automatic garbage collection, while C and C++ require manual memory management. Optimizing memory usage can include practices like reusing objects, using memory pools, and employing data compression techniques. Performance optimization involves improving the efficiency of your code by reducing time and space complexity. General optimization strategies include loop optimization, reducing redundant calculations, and optimizing algorithms. Machine level optimizations focus on using platform specific features, while cache optimization improves data retrieval speeds by leveraging the system's cache memory effectively. Concurrency and parallelism are vital techniques for optimizing performance in multi-threaded applications. By dividing tasks into smaller, independent units, you can execute them concurrently to speed up processing. Handling synchronization and avoiding deadlocks are crucial challenges in parallelism. Optimizing concurrency models helps achieve better performance and scalability in modern applications. Compilers play a significant role in performance optimization. Various techniques such as constant propagation, loop unrolling, and inlining can be applied by the compiler to improve execution speed. Optimizations like vectorization and using SIMD single instruction multiple data enhance performance on multi-core processors. Compilers also offer different optimization levels such as O1, O2, or O3, allowing developers to balance between compilation time and execution speed. Profiling and benchmarking are critical tools for identifying performance bottlenecks. Profiling tools like gprof, visualvm, and cprofile allow you analyze the runtime behavior of your application. Benchmarking tools such as time and benchmark.js help you measure execution time, scalability, and resource usage. By identifying performance bottlenecks, you can focus on your optimization efforts where they matter the most. Choosing the right data structure can greatly impact performance. For instance, using a hash table instead of a list allows for faster lookups. It's important to understand the trade-offs between different data structures like arrays, linked lists, and trees, and select the one that best fits the problem you are solving. Efficient data structures can reduce both memory usage and processing time. In real-world applications, optimization techniques have a profound impact. For example, search algorithms like binary search outperform linear search in sorted datasets. Database query optimization through indexing and query planning improves performance in large datasets. In web development, optimizing the DOM using lazy loading and implementing caching strategies can significantly improve the speed and responsiveness of your web application. To summarize, optimization is crucial for enhancing the performance and efficiency of your software. Whether it's through memory optimization, performance tuning, or leveraging compiler optimizations, the right techniques can help make a significant difference. Don't forget the importance of profiling and benchmarking in identifying areas to optimize and refine. Thank you for your attention. We have covered several topics. on optimization techniques across different programming languages. Now, I would be happy to answer any questions or discuss specific optimization challenges you have encountered in your own projects. Welcome to today's presentation on language evaluation. In this session, we will dive into the criteria for assessing programming languages, explore evaluation methods, and discuss real-world studies. I am excited to guide you through this topic. Here's a quick look at our agenda. We will begin by discussing the criteria for evaluating programming languages. Then we will move on to the evaluation methods and metrics, followed by real-world case studies. We will also look at industry adoption and practical considerations before wrapping up the challenges in language evaluation. Let's start by looking at the criteria for evaluating programming languages. We consider factors like readability, which focuses on syntax and clarity, and reliability, which involves things like type systems and error handling. Efficiency looks at performance and optimization, while maintainability emphasizes modularity and long-term support. Next, we discuss the methods and metrics used for evaluation. Theoretical approaches involve formal semantics and grammar, while practical approaches rely on performance benchmarking tools and developer feedback. Both perspectives are crucial when assessing the effectiveness of a language. Now let's examine some real-world case studies. Rust versus C++ demonstrates how Rust focuses on memory safety while C++ offers low-level control. JavaScript versus TypeScript shows how static typing in TypeScript enhances development workflows, and Python versus Java highlights simplicity versus scalability in language design. Industry adoption plays a significant role in the evolution of programming languages. A language ecosystem, including its frameworks, libraries, and community support, can determine its success. For example, Python's extensive ecosystem in machine learning, with libraries like TensorFlow and Pandas, has greatly contributed to its popularity. Evaluating ecosystem factors is also essential. A language ecosystem influences its adoption. Strong ecosystems provide developer tools, libraries, and active community support, which in turn drive a language's success and longevity in the industry. However, language evaluation does come with challenges. For one, there's the risk of bias due to developers' personal experiences with certain languages. Readability can also be subjective, as different developers have different preferences. Additionally, there are no universal benchmarks that apply to all languages and use cases. By the end of this session, you should be able to understand the factors that affect the effectiveness of a programming language, use both theoretical and practical evaluation methods, critically compare languages based on various factors, and discuss the long-term impacts of language design choices. For your homework or project, I recommend a comparative evaluation project. Choose two programming languages, evaluate them based on their readability, reliability, efficiency, and maintainability, and present your findings with real-world use cases examples. In conclusion, we have covered the essential aspects of language evaluation, including the criteria, methods, use cases, case studies, and practical considerations. It's clear that evaluating programming languages is a multi-phased task, and understanding these factors will help you make more informed decisions when choosing a language. Thank you for your attention. Now I would like to open the floor for any questions you may have. Please feel free to ask anything related to the topics we have covered today. Hello and welcome to this presentation on Trends in programming languages. Today, we will explore the evolving landscape of programming languages, modern trends, the rise of new languages like Rust and Go, and the impact of AI on language design. As we dive into the trends, we will first cover the key areas influencing the world of programming languages. Modern trends include the rise of functional, declarative, and hybrid programming paradigms. We will also discuss new languages like Rust and Go and examine how AI is reshaping the way languages are designed and optimized. Functional programming has gained significant traction in recent years. With its core principles of immutability and pure functions, functional programming like Haskell, Scala, and F Sharp help reduce side effects, making concurrency easier to manage. Languages like Python have also adopted functional features, making functional programming more accessible to a broader audience. On the other hand, declarative programming focuses on what you want to achieve rather than how to do it. This leads to simpler, more readable code. Languages like SQL, HTML, and C++ excel in declarative programming, where the programmer declares the logic without specifying control flow. This approach is widely used in cloud computing, APIs, and web development. Hybrid programming languages are increasingly popular. These languages combine multiple paradigms, giving developers the flexibility to choose the best approach for the task at hand. For example, Python supports functional programming constructs, while Java has adopted lambda expressions from functional programming. Rust, a language designed for system-level programming, is making waves due to its focus on memory safety and performance. Rust's unique ownership system eliminates data races at compile time, offering significant advantages for concurrent programming. It ideal for it's ideal for use cases like WebAssembly, game development, and low-level system design. Go, developed by Google, is another rising star. With its simplicity and speed, Go excels in handling concurrency with its core routines. It's ideal for cloud computing, microservices, and network applications. Go's design emphasizes ease of use and efficient resource management, making it a popular choice for modern infrastructures. AI is starting to play a crucial role in programming language design, from AI-driven code optimization to the development of new paradigms. AI is enhancing language features and improving compilers. As machine learning and AI technologies evolve, we can expect even more innovations in the design and implementation of programming languages. Machine learning and AI are transforming the way we write and optimize code. Tools like auto-completion, intelligent debugging assistance, and code generation are powered by machine learning. These tools make developers more work more efficient, and the future we may see even more sophisticated AI-driven programming environments. Domain-specific languages or DSLs are tailored for specific industries or problem domains. By providing highly specialized syntax and semantics, DSLs simplify coding tasks. Examples include TensorFlow for machine learning, R for statistical computing, and SQL for database queries. DSL improve productivity and allow developers to focus on problem, not the language. An interesting trend is the integration of low-level features in high-level languages. For example, Rust's memory management system gives developers fine-grained control over memory without sacrificing the productivity of a high-level language. This combination of low-level control with high-level abstraction is becoming a powerful tool for modern software development. Finally, there's a growing emphasis on code readability and maintainability. Modern programming languages are designed to be clear, simple, and easy to understand. Tools that enforce code style, along with features like clear syntax and powerful IDEs, help developers maintain cleaner, more efficient code bases. In summary, programming languages are constantly evolving. We see a rise in functional and declarative programming, with languages like Rust and Go leading the charge. AI is significantly sharpening language design, and DSLs are streamlining domain specific tasks. Additionally, the integration of low level features in high level languages is giving developers more control without compromising productivity. To conclude, the future of programming languages looks exciting, with AI driven evolution, hybrid paradigms, and powerful new tools paving the way forward. Staying updated with these trends will be essential for any developer looking to stay ahead in the ever evolving world of programming. Thank you for listening and feel free to reach out with any questions. Welcome to day 36, the future of programming languages. Today we will explore predictions, trends, and the challenges facing the evolution of programming languages. Let's dive in. In this session, we will focus on several key topics: predictions for language evolution, the role of machine learning and AI in language design, emerging paradigms and features, the impact of new technologies, and ethical considerations. We will also look at the challenges and opportunities for language development in the future. As we look to the future, we can expect increased abstraction in programming languages, making them easier to learn and use. Domain-specific languages (DSLs) will rise in popularity, catering to specific industries, while cross-platform development will see languages like Kotlin and Rust lead the charge. Furthermore, machine learning will begin to play a significant role in optimizing code and enhancing the programming experience. Machine learning and AI are poised to revolutionize programming languages. In compiler design, AI will help auto-tune code for hardware efficiency. Additionally, AI-powered tools like codecs will assist in code generation, while real-time bug detection and intelligent debugging will make coding faster and more reliable. The next generation of programming languages will introduce features such as AI-driven programming, enabling the creation of languages tailored for machine learning. We will also see self-optimizing languages that automatically enhance their own performance during runtime. Concurrency and parallelism will be simplified, and specialized languages for quantum computing will begin to emerge. New technologies will have a profound impact on language design. Blockchain will influence languages like Solidity for decentralized applications. Cloud native programming languages will be optimized for cloud environments, while languages for VR AR development will evolve to handle 3D object manipulation. Languages will also be tailored for edge computing, enabling more efficient distributed systems to IoT applications. Ethical corners will play an increasingly important role in the development of programming languages. Designers will need to focus on privacy, security, and inclusivity, making languages accessible to a broader range of users, including those with disabilities, and considering the cultural impact. of programming languages will be critical for ensuring that technology remains beneficial for all. The development of new programming languages will face several challenges such as maintaining backward compatibility with older versions. Security concerns must also be addressed, ensuring that new languages are resistant to vulnerabilities. However, these challenges present unique opportunities to innovate, particularly with AI-driven security and language optimizations. As programming languages evolve, so too will the role of developers. The future will see a shift from coding syntax to high-level program problem solving and application design. Developers will focus more on logic and abstract design rather than dealing with low-level details. Continuous learning will be essential as new languages and tools emerge in response to technological advancements. To recap, key trends in programming languages include the rise of AI and cloud native development, the growing importance of specialized paradigms, and a focus on security and ethics. These trends will shape the future of software development and how we interact with technology. In conclusion, the future of programming languages keeps promising with new advancements on the horizon. As developers, it's important to stay updated on emerging trends, participate in the design of new languages, and be ready to adapt to new technologies as they arrive. Thank you for joining me in this session. Now, I would love to hear your thoughts and answer any questions you may have. Please feel free to ask anything related to the topics we have covered today. Welcome to the Language Design Project. In this session, we will explore a practical approach to designing a new programming language. Let's dive in and learn how we can create a language from scratch. Today, our objective is to design a new programming language focusing on the syntax, semantics, and basic features. This hands-on experience will help you apply the concepts you have learned throughout the course in a real-world context. Why would you want to design a language? By understanding the trade-offs in language design, we can better appreciate the thought process behind popular languages. We will also look at the challenges faced by language creators and how their solutions impact software development. Language design involves several key steps. First, we define the purpose of the language. Then we design the syntax and structure of the language. Finally, we define the semantics, how our constructs will behave and interact with the system. Let's break this down further. The first step is to define the purpose of your language. What problem will it solve? Is it a general purpose language or a domain specific language focused on a particular application like web development or scientific computing? Understanding the target audience is crucial here. Next, we move on to designing the syntax. This includes defining the structure of valid statements and expressions. Will your language be case sensitive? Will it use indentation like Python or braces in C? Think about how control structures like loops and conditionals will look in your language. Once the syntax is defined, the next step is to focus on semantics. This is about determining what each construct in your language means. How will loops behave? What's the memory model of your language? Will it use automatic garbage collection or will the programmer manage memory manually? Now let's think about the key features of your language. What paradigms will it support? Is it imperative, functional, or object oriented? What features will make your language unique and stand out from the rest? Designing a language involves using several tools and frameworks. You will need to create a prototype using an interpreter or a framework. There are also there are also tools like Antler or Lex and Yak to help the parsing process. Once the language is designed, documenting its grammar, syntax, and semantic is essential. Now it's time for the practical exercise. You will be working either individually or in small teams to design a programming language. You will need to focus on defining the purpose, syntax, and semantics of your language. Keep in mind the trade-offs in language design. After completing your design, you will share your language with the class. You will discuss the rationale behind your decisions, such as why you chose a particular syntax or memory model. It's a great opportunity to learn from each other and get feedback. As we wrap up, we will have an open Q&A session to discuss any challenges you faced during the design process. We will also review how different programming paradigms influence the way we design languages. You will gain a deeper understanding of the language design process. For your assignment, you will submit a language specification document. This document should include your language purpose, syntax, grammar, and semantics. Be sure to outline key features and any innovative aspects of your language. Thank you for your attention today. If you have any questions, feel free to ask. Remember, designing a language is an exciting and challenging task that requires creativity and deep understanding of programming concepts. Best of luck for your projects. Welcome to today's session on language case studies. In this presentation, we will explore real-world examples of programming languages, their design decisions, and their impact on software development. Let's dive in. Today, we aim to dive deeper into real-world examples of programming languages. We will explore how different languages have evolved over time, learn from their successes and failures, and understand the design and applications of some of the most popular programming languages. Language case studies are essential as they provide insights into how theoretical language design meets practical application. By analyzing successful and unsuccessful languages, we gain a better understanding of the decisions made during their design and the trade-offs involved in language development. Our first case study is C, one of the most influential languages in the history of computing. Designed for system-level programming, C emphasizes performance and control over hardware. Its strengths lie in its simplicity, portability, and efficiency. However, it lacks built-in safety features and manual memory management can lead to errors. C has been crucial in operating systems, embedded systems, and hardware programming. Next, we have Python, a high-level interpreted language known for its readability and ease of use. Python has become the go-to language for beginners due to its simple syntax and vast library support. While it's slower than compiled languages and relies on dynamic typing, its real-world applications are vast, from web development to data science, AI, and automation. Java, designed for portability with the Java Virtual Machine (JVM), follows an object-oriented paradigm. Its strengths include robust memory management, a rich library ecosystem, and cross-platform capability. However, its syntax is often seen as verbose and it tends to be slower than languages like C and Go. Java remains widely used in enterprise applications, Android development, and large-scale systems. Rust is a systems programming language that prioritizes memory safety without sacrificing performance. Its strength lies in preventing memory errors like null pointer dereferencing and buffer overflows. Thanks to its ownership model, while Rust's learning curve can be steep, it's well suited for performance critical applications, WebAssembly, and embedded systems. Go or Golang was designed for simplicity and high developer productivity, focusing on concurrency and ease of use. It offers a simple syntax, fast compilation times, and built-in concurrency via Go routines. Despite its strengths, Go lacks generics and a more extensive standard library. It's popular for cloud computing, backend systems, and microservices. In this slide, we compare the case studies we have discussed. We will see that each language design decisions are influenced by different priorities: performance versus productivity, memory safety versus control, and cross-platform compatibility. Rust and Go are modern languages addressing limitations of older languages like C and Java, bringing new concurrency models and memory safety features. Now it's your turn. For this exercise, choose one of the languages discussed today and justify its best use cases based on its design features. Additionally, consider which language would be the best fit for a specific domain, such as systems programming or web development. Feel free to discuss your thoughts with your peers. Programming languages have a long-term impact on industries, software development practices, and the overall tech ecosystem. By understanding the real-world applications of these languages, we can make informed decisions about which language to use in different contexts. To conclude, understanding the history, strengths, and weaknesses of programming languages helps us become better developers. Today, we have covered the key takeaways from our case studies, from language design decisions to real world applications. I encourage you to explore further and experiment with different languages to deepen your understanding. That brings us to the end of today's presentation. I would like I would now like to open the floor for any questions or feedback you may have. Feel free to ask about the case studies, language features, or anything else related to programming languages. Welcome to today's presentation on ethical and social considerations in language design. In this section, we will explore the importance of ethics in programming languages, their social impact, and how developers can contribute to responsible language design. Let's dive into how programming languages influence both society and the development community. Ethics in programming is about understanding the moral implications of the languages we create and use. Ethical considerations play a key role in how programming languages are designed, influencing both society and developers. By considering these ethics, we can promote responsible design that benefits the greater good. Let's take a closer look at why this is so important. Inclusivity is a fundamental aspect of modern language design. We must ensure that programming languages are accessible to a wide range of users, including those with disabilities. This also involves supporting multiple languages and character sets for global use. Additionally, gender neutral language promotes equality in our code, ensuring that terminology is inclusive for all programmers. Programming languages can inevitably introduce ethical dilemmas, especially when it comes to security and privacy. For example, certain language features may create vulnerabilities, allowing malicious actors to exploit weaknesses. Bias in language design can also affect fairness, particularly in AI and machine learning applications. It's essential that developers recognize and address these ethical issues to create more secure and equitable languages. The impact of language design goes beyond technical features. It also affects developers and users. Developers must take responsibility for the languages they design, ensuring that they promote transparency and fairness. The choice of language can also impact job opportunities as some languages are more widely adopted than others. Lastly, programming education plays a crucial role in shaping how developers understand and implement ethical considerations in their work. Programming languages don't just affect code quality, they also have environmental implications. Energy efficiency in language design can reduce the computational power required to run applications, which is particularly important in resource constrained environments like IoT devices. As software development practices evolve, we must also consider sustainability and the ecological footprint of our programming decisions. As programming languages evolve, we face important ethical decisions such as whether to prioritize open source development or proprietary systems. Open source languages foster collaboration and transparency, while proprietary languages may limit access and innovation. The process of language evolution often involves addressing challenges from older systems and integrating new paradigms requiring careful ethical considerations. An ethical review process is crucial for ensuring that new languages are designed with moral responsibility in mind. Ethical committees can guide language developers in identifying and addressing potential issues such as biases or harmful constructs. Case studies of languages that have faced ethical scrutiny can provide valuable lessons for future language design. The importance of ethical considerations in programming languages will only continue to grow. As new technologies emerge, such as AI and machine learning, they will introduce new challenges for language designers. Developers must stay aware of these issues and work towards solutions that prioritize fairness, transparency, and social responsibility. The future of language design lies in its ability to adapt to the ethical demands of our rapidly evolving world. Thank you for your attention. If you have any questions or would like to discuss any of these topics further, feel free to reach out. I am happy to answer any queries you may have. Remember, responsible programming language design can help shape a better future for everyone in the development community and beyond. Welcome to the presentation on the challenges in modern language development. Today we will explore some of the key issues in programming language design and development, as well as their future directions. In this presentation, we will provide an overview of the key challenges in programming language development. We will discuss how languages evolve to meet the demands of new paradigms, hardware advancements, and security concerns. One of the major challenges in modern language development is ensuring backward compatibility. As new versions of a language are released, they must support old code to avoid breaking existing applications. Some strategies used to maintain compatibility include deprecation, versioning, and maintaining compatibility layers. However, managing legacy code like COBOL or Fortran remains a challenge for many organizations. As programming languages evolve, there's an increasing need to integrate multiple programming paradigms such as imperative, object-oriented, functional, and concurrent programming into a single language. This integration presents challenges including cognitive overload for developers and maintaining simplicity. Languages like Scala, C++, and Rust have made strides in this area by supporting multiple paradigms. Security is a critical concern in modern language development. Languages must include features that prevent vulnerabilities like buffer overflows and SQL injections. For example, Rust provides memory safety with its ownership and borrowing system. Modern languages also address security through features like sandboxing and execution models, ensuring safer execution environments. Concurrency and multithreading present significant challenges in language design. Race conditions, deadlocks, and ensuring thread safety are common issues. Modern languages like Go and Java have introduced models like Go routines and threads to manage concurrency. However, balancing efficient concurrency models while avoiding complexity remains an ongoing challenge. Hardware advancements such as the rise of multi-core processors and GPUs have influenced language design. For example, languages like CUDA have been developed to utilize GPU capabilities. However, the challenge is to balance performance optimization with portability. Languages must evolve to make the most of new hardware while remaining compatible across different platforms. Another key challenge is maintaining a balance between developer productivity and performance. High-level abstractions often improve productivity, but they can come at the cost of performance. For example, languages like Rust prioritize performance without sacrificing developer safety. Striking the right balance is essential for creating languages that are both efficient and easy to work with. To recap, we have discussed several key challenges in modern language development, including backward compatibility, the integration of old and new paradigms, security, concurrency, hardware adoption, and balancing productivity with performance. These challenges shape the evolution of programming languages. Looking forward, we expect programming languages to continue evolving in response to new needs and emerging technologies. The integration of AI and machine learning in language design will likely bring new paradigms and capabilities. However, ongoing challenges related to complexity, security, and performance will remain key considerations in the development of future languages. Thank you for your attention. If you have any questions or feedback, feel free to ask. I would love to hear your thoughts on this topic. Welcome to Day 41, a review of key concepts in the Principles of Programming Languages course. Today we will be summarizing the major topics we have covered throughout the course and preparing for our final wrap-up. Let's begin by reviewing the major topics we have explored. First, we have discussed the foundational concepts of syntax and semantics and how these shape the structure and meaning of programming languages. We then dove into types and type systems, looking at the differences between strong and weak typing and static versus dynamic typing. Memory and variables were also key aspects we studied, including stack versus heap memory and the importance of garbage collection. We also covered control structures like recursion, loops, and conditionals, as well as the different programming paradigms, including imperative, declarative, and object-oriented programming. Now let's shift focus to language design and implementation. We looked at the role of language design, how compilers versus interpreters work, and the different phases of language implementation, from lexical analysis to code generation. We also discussed how runtime systems such as JVM and CLR manage memory and execute code. Next, we reviewed two critical areas of programming: error handling and concurrency. We explored the different types of errors, syntax, runtime, and logical, and how exceptions are handled in languages like Java, Python, and C++. On the concurrency front, we delved into how modern languages manage threads, processes, synchronization, and potential issues like deadlock. Moving on to the advanced features found in modern languages, we explored coroutines and the async await pattern for asynchronous programming. We also covered metaprogramming, where code can modify itself, and reflection and introspection, which allow a program to examine its own structure. This is the perfect time for an open Q&A session. If there's anything you would like to clarify about key concepts like memory management, programming paradigms, or error handling, feel free to ask. Let's dive into any lingering questions you may have. Let's take a moment for a group discussion. Think about how the concepts we have learned today apply in real world scenarios. How do different languages handle memory management and concurrency? How do you select the right language for a project based on its strengths and weaknesses? We have certainly encountered challenges during this course. Some of the major ones include debugging in dynamic versus static languages and managing concurrency in multi-threaded environments. Today we will discuss some practical solutions to these challenges that will help you in your programming journey. As we wrap up, here are the final takeaways. The importance of abstraction, modularity, and efficiency has been evident through the course. You should now have a deeper understanding of memory management, type systems, control structures, and the impact of different programming languages on software design. The key to success in programming is continually applying these concepts and choosing the right tools for the task. Don't stop here. Continue your journey with additional resources for further learning. There are numerous books, online courses, and practice platforms such as LeetCode, HackerRank, and CodeWords that will help you strengthen your knowledge and skills. Keep challenging yourself with new problems and languages. Finally, we have reached the course wrap up. Reflect on the path we have taken, the skills you have gained, and the concepts that will shape your future programming projects. We have covered a wide range of topics that prepare you for careers in language design, software development, and more. Keep exploring and thank you for participation in this course. Welcome to day 42 of the Principles of Programming Languages course. In today's session, we will recap key concepts, explore future learning paths, and discuss career opportunities related to programming languages. Let's begin by revisiting the major topics we have covered in this course. We explored syntax and semantics, diving into how structure and meaning work in programming languages. We also learned about various programming paradigms such as imperative, functional, and object-oriented programming. We examined type systems, memory management techniques, and key language implementation concepts like lexical analysis and code generation. Additionally, we explored concurrency, parallelism, and modern programming features like async, await, and meta-programming. Before moving forward, we will take some time for a Q&A session. Feel free to ask any questions lingering or clarify any concepts that you might have found challenging. This is your chance to review topics that may need more attention, such as the differences between static and dynamic typing, or how paradigms like functional and object-oriented programming can impact code design. As you continue your journey in programming languages, here are some resources to further deepen your knowledge. Books such as Concepts of Programming Languages by Robert W. Sebasta and Programming Language Pragmatics by Michael L. Scott are excellent reads. Online platforms like Coursera, edX, and Udacity offer courses to continue your learning. Additionally, academic papers from conferences like POPL and journals from ACM, SIGPlan can provide cutting-edge research in the field. To practice what we have learned, consider using tools like GCC for C, C++, JVM for Java, or Haskell's GHC for functional languages. Online IDEs like REPL.it, and Glitch offer easy access to scripting languages like Python and JavaScript. And practice platforms such as HackerRank, LeetCode, and CodeWords are fantastic for honoring your problem-solving skills and learning new concepts in a hands-on way. Programming languages open up a variety of career paths. As a software developer or engineer, you will be working with languages to develop everything from backend systems to front-end interfaces. If you are interested in language creation, you can pursue a career as a compiler engineer or language designer. There's also the option to work as a researcher, contributing to new theories and advancements in programming languages. Another option is software architecture, where you will apply your language knowledge to design scalable systems. Let's reflect on the course. We have covered a wide array of topics that give you a strong foundation in understanding how programming languages work. Moving forward, I encourage you to keep experimenting with different languages and paradigms. Your feedback is also incredibly valuable. Please share your thoughts on how this course can be improved or topics you would like to explore further. As we wrap up, I want to leave you with a motivational quote. The more you learn, the more you realize how much there is to discover. Programming languages are vast, and there's always more to learn. Keep staying curious and apply your knowledge to solve real world problems. Thank you all for your participation, and I wish you all the best in your future programming endeavors. Before we conclude, are there any final questions? This is your chance to clear up any doubts or share your thoughts about the course. I am here to help and address any lingering questions you may have.